Yes, we see you. She sees us. Yes, perfect. Yeah, we had to switch channels.
Did anything change with the projector? Stefan? Did anything change with the projector?
We have to reset the cable. I think it's best if you replug your adapter.
Okay, I tried. I'm unplugged now. So, if you want to reset.
I will look for another adapter.
It worked a second ago, like usual. Everything's good. Oops. It's okay, I used the microphone, don't worry about it.
Where did you put the table? Oh, thank you.
If this doesn't work, we can use the mic here.
Ah, there was sound. Perfect. Start a little bit lower. Just one channel, but it's okay.
It's way better, yeah. Video signal.
It's not.
No start. Had to reboot the transcoder.
Hmm?
Okay. So this is not working. It is, but you must not step onto the panel.
That's
So
a requirement. Yeah, the only thing was to. Okay, let's try this again. There we go.
okay.
Can I unplug and plug it? Let me test.
Hello, it's me.
Yeah, it works.
It is you.
Hi, Wendy. Can you write a little bit for a test? Can you continue writing? Hello, 1, 2, 3.
Absolutely.
It's hello. Good morning. Okay, it looks well on the screen.
Okay, yeah, I'm not I'm ready. Yeah. Can you
Yeah,
pull out the cable?
yeah, it looks
Just make
well.
a huge noise.
Yeah. Okay. Okay, can you clean up? Thank you.
We're testing Neville's setup now. Would you like to have a stick or stand really close to this one, or
Maybe let me try that. The overhead one. The laptop is gigantic.
that's
I really need like a in the future. Yes?
well?
Yeah, that's fine. Fine. Okay. What do I say?
Just say hello.
Hello. Something. I'm kidding. Okay, cool. I think this is fine.
This is fine.
Yeah. This is
HDMI. Do you need to power your laptop? You have sockets down there.
30 minutes.
Yeah.
Okay.
Mirror mode.
Cool. Happy? Just wanna see. Yeah, that's fine. I'm good.
Just leave. Right. Do we have slides? We finished tech setup. Can we switch to the timetable, please?
So I'll just stay here then. Yeah. I'll try not.
Just please don't step on that.
Yeah.
So if
Good morning, everyone. We are about to start, so if everyone could grab a seat. 1 minute.
Ladies and gentlemen, please take your seats. The conference is about to start.
Good morning, everyone. Welcome again. I hope you all had a very nice breakfast and a nice commute here. Today, we have a great lineup of talks and workshops, yet again. Also, I want to note the venue is really nice this year. Haven't had a conference in this nice a venue as of yet, so nice. I also want to thank the staff for organizing all of this, of course, our sponsors, and of course, you as well for being here. Thank you. If you have any feedback, we do have a feedback box at the check-in upstairs. So just write it on some paper. It's quite anonymous. Also, if you have feedback about any of the talks or the workshops, put it in the box. You can also mail us, but that's maybe not as anonymous. So I was wondering about one thing. Rust has some unique features. Some languages share these features, but I'm wondering, how many of you, raise your hand, have used async await yet? Well, that's quite a lot. How many have tried to program on an embedded device and run Rust? Maybe because the workshop is more hands now, but and how many of you have tried running WebAssembly? That's also a lot. Wow. Okay. Maybe an old crowd here, or maybe I should change my expectations. So this morning I came here by metro. First thing I noticed when I entered the metro in Barcelona, it's very hot. Like, maybe I heard it's because of the brakes. Every time a metro brakes, it emits heat. So the entire space is warmed up by all the metro trains braking all the time. And they don't have this problem in London because they charge like the electricity network again when they brake. Saves about 5 degrees centigrade. So maybe they should try it here as well, especially in the summer. The second thing I noticed when I went into the metro is they have these very nice indicators over the platforms indicating when the tram will arrive. So I'm used to like indicators saying, oh, somewhere around this minute, and it's late for 5 minutes. But here they gave like an exact second when the tram would arrive. I also saw they were cheating because they added like 30 seconds on the last moment. But still, I would love to have those indicators as well. What would be even greater is to have an API just providing this information for buses and trains and trams. In my country, they have this API, but it's kind of shitty. But of course, in a lot of countries, they don't have this. Also depends on the company, I guess. I hear that in some countries, it's really bad. Like that you can get a delay of an hour and don't know what's happening for an hour long. Well, you could ask your company, hey, could you provide me an API of this information? You have this information, right? But Neville actually decided to do something about this and crowdsource this information. So he's going to give a talk about how he made this system for crowdsourcing this information in Rust. Give a warm welcome to Neville.
Morning, everyone. Today's talk is going to be about powering crowdsourcing of public transit delays with Rust. Morning, everyone. My name is Neville Dipale. Sorry about that. My name is Neville Dipale. I'm from South Africa. My Twitter handle is Nevi_me. I'm working as a data engineer, so mostly a freelancer. I started programming as a hobby about 10 years ago now. I run a public transit information service in South Africa, so mostly in my region, Gauteng. I started using Rust about half a year ago, and I recently, as in a few months ago, became an Apache error committer, contributing to the Rust implementation. So in our agenda today, we're going to be talking about trains in our region and challenges with them. So I'll give you an overview of how they work, etc. I'll talk about the crowdsourcing solution, how we use Rust, and what the benefits of having used Rust are. So as a background with our train service, we've got 2 train services in our region. Out of interest, how many people have been in South Africa by a raise of hands? Oh, cool, thanks. So we've got two trains. We've got the fast train and the metro train. The fast train was actually built for the 2010 Soccer World Cup. We hosted it and win it. The metro train has been around since around the 80s, so it's got very aged infrastructure. They haven't replaced some of the trains in quite a long time. The metro train is very cheap, where you can get from one side of the province to the other side of the province about 2 to 3 euros, and then most trips will be 1 to €2. When the fast train is a bit more expensive, so it goes from the airport into the city, and you pay about 10 euros at times for the train. So the metro train is used mostly by poor communities and students who rely on the service. So let's guess which train is which here. You've got this one, which would be fast train, and then you've got this one being the metro train. So we've had this problem for a very long time where, because there aren't enough trains, they get overcrowded and people get desperate to get to work, and then they hang on to the trains. They are changing that now with new metro trains, but we've had problems over the years with procurement, government issues, etc. We were supposed to have these new trains about 4 years ago. I think now there's only 3 running, and they've promised that we'll have all of the trains being replaced by these ones in the next 10 years. So the struggle is still going to continue. Okay. So with metro train delays, they've got severe infrastructure issues, as I've mentioned. It's estimated that 40% of rolling stock, i.e. the train coaches, are out of service, are not available, and this affects peak time services quite significantly. It's only during the day when there's fewer people taking trains, fewer services, where they get to catch up, and then the same problem then begins again in the evening. The trains can get stuck in the middle of the tracks, cable theft, signaling problems, etc. It's not uncommon for you to be on the train, stop in the middle of nowhere for like 15 to 20 minutes, and then the train continue again. So I did an interesting analysis, not here though, for something else, where we were looking at the average train travel times based factoring into account the delays. And one of the trains took about, I think it traveled at 30 kilometers an hour effectively, and it was traveling about 100 kilometers. So you can imagine how long that train trip was. Commuters experience delays with over 60 minutes in most cases. Part of my pitch was, I said, it was quite dramatic. I said, your train is arriving in 20 to 90 minutes, because that's a kind of uncertainty that people end up having. There's communication issues also from the operator. We don't have, none of it is digital. All of it is analog. We don't have an API that provides information or such. And a lot of the times, even for the trains to move themselves, they rely on phones. The train conductor will stop the train and say, can I move on? And then they have to wait for like 10, 15 minutes or so. In the past few years, we've actually had a number of collisions of trains. There was one big one where I think 20 people died or so. So it's been very bad over the years. Okay. And then here's a graphic that just shows some of the data that we've collected. I've split it into delays. It's a histogram of delays where each bucket is 5 to 10 minutes. So the first two buckets there are the trains that are early or on time. And in the 10-minute category, you've got 53% of the trains being delayed by up to 10 minutes. So this is great, but also bear in mind that we don't crowdsource the entire network. So it's only a snapshot of some of the trains. And then you'll see that the delays sort of go down. I think this would be a log normal distribution. So you still have quite a number of trains that are very late in most cases. And each time, this is normally either in the morning, somebody has to get to work or a meeting at 8 a.m. They end up getting there at 9. As a result, a lot of people have actually lost their jobs because you'd come late every day in a week, and then your employer just says, well, sorry. There are people who wake up at 3 a.m. just so that they can get to work at 8 a.m. in the morning, which is quite terrible. And then the same again happens at night, where people would leave work at 5 p.m. if you work at 9 to 5, and then only get home at 10 p.m. Okay, so our solution has been to provide metro commuters with information on train delays. We use Twitter and push notifications on an Android app. So we've got an Android app that people use to crowdsource this information. We crowdsource the delays either by sharing a train trip or spotting trains. So if you would have noticed on the on that picture of the metro train, there's normally 4-digit numbers on each train, and we use those, we map them to the schedule, and then people just provide us what the train number is, and then we figure out which train it is. We calculate the delays based on the actual versus schedule. So the actual algorithm is quite simple because we're just currently using a linear model where we say if the train was supposed to be here 5 minutes ago and the average speed has been, let's say, 20% less than what it should be, we just do a simple linear progression of what the delays would be. And then we generate estimated arrivals at train stations and then notify commuters about delays. So this is what we use Rust for. Okay, so in terms of submitting train delays, the architecture is quite complex. There's a lot of services that are running around because I've been doing this for about 7 years now. Some of the stuff is in Rust, a lot of it is not in Rust, but for the talk, I'm just going to talk about the few components, specifically 3 components that are built in Rust. We've got a location sample service that checks for sample validity and accuracy. So imagine when you're crowdsourcing, one of the problems that you have is that some information might be accurate, some might not be accurate. There's nothing stopping a person from saying I'm on train 1235 instead of train 1234, and then they give you incorrect information. One of the things I saw in the early days of deploying this was a train that was moving in reverse. And it took me a while to figure out that, oh, somebody's actually on the other train, but they're submitting train locations for this one, so it looks like the train just keeps going backwards. Then this location sample deals with that. We've got a service that then it saves the samples in the database. I'll explain a bit more in detail about that. Then you've got a vehicle stream service. If you were in Rust Lab in Italy, I talked about specifically the vehicle stream service. It calculates delays from samples every 7 seconds and then generate locations and delays of trains. The user sent delays from samples, and then other users are notified of delays. I'll talk about this in detail. So here's an example of the process. So let's say you've got train A that's expected at station 3 at 8 a.m. There's no samples yet, so we're just relying on schedules. A user's waiting for the train, different users are waiting for the train at station 4, 5, 6, 7. And then those are the estimated arrivals at those stations. So once we receive our first sample, let's say the sample is at 8:12, and then that's between station 3 and station 4. Already for station 4, there's a delay, so we'll just project those. And then I've marked them in red to show the users that we're notifying. One of the problems is that we don't want to spam users and notify them every other minute to say, well, the train was arriving in 4 minutes, now it's 3 minutes, etc. So we project those, and then at the next sample that we get, we only then calculate the difference in delays. If the delay is still more or less the same, we use a 5-minute range, we don't notify the user again. So when you get a next sample at 8:16, we'll then say, well, the station 4, the train has already passed, it was at 8:14. In the next one, it's at 8:25. It's within a 4-minute difference from 8:21, so we're not going to notify the user. And then we're only going to notify the user whose train is now arriving at 8:33. Okay. So in terms of the Rust services themselves, the location sample is a gRPC server that uses Tower gRPC. It receives vehicle samples and then just processes them. It matches samples to trains, so we take the 4-digit train number and then we match it to the train, and then we generate a last known location. It uses Actix to monitor the state of the users and trains. I'll talk a bit more about what I use Actix for. I know Actix Web is more popular than Actix itself. And there I've just shown a screenshot of a trip executed. It's effectively the state that I manage for the application. Okay. So we've got a trip status struct that tracks the last known details of each trip. So going back to the previous slide there, you see that we've got user trips and trips. A user trip just matches the user to say the user is on this train. So when they submit another train sample, we automatically reject it because you can't be on 2 trains at the same time. And the trip just tracks the overall status of a trip. So in the trip status, you'll see we've got the trip ID, the route ID, the last distance, and then location and other information. The last distance is very important because we calculate the distance based on the geometry of the trip. So if somebody submits a sample and says that the train is close to station 3, let's say it's 2 kilometers away from station 3, and another user submits a sample 5 minutes later saying, actually, it's close to station 2, we're going to reject the second sample because the train can't go back in reverse. So that's how we work around that issue. And then we also keep track of congestion and occupancy. It's what Google does. We're hoping that with a lot of users, then we can be able to reliably tell people that your train is actually full. It's better maybe to wait for the next one if it's coming. Okay. So we we've got an Actix actor that receives a sample and handles it. The benefit here is that I don't have to worry about multi-threading because Actix has a mailbox that just stores samples. So as long as I've got a big enough mailbox to handle capacity, then all the samples just keep coming and getting processed. One benefit of Rust is that it's very fast, so I never have a big backlog at any point in time. The sample just produces a location or an error if there's an error. For example, the location is invalid. Okay, so after the service saves the valid sample onto the database before it returns it to the client, this sample then gets picked up by the next service that I'm going to talk about. And here's how a sample looks. If you work with geospatial data, it's vehicle coordinates and then some information about the vehicle. Okay, so the next service that I then use is the vehicle streams. So the streams just reads data from a database periodically every 7 to 10 seconds, and then it projects the delays per route. So this is for estimate and live scheduled services and live services. It just calculates the estimates and keeps churning them out throughout the day. It starts running from I think 2 a.m. when the first train moves up until 11 p.m. when the last bus is moving. So it's both for trains and buses. It sends all the results to a PubSub service. I use nets.io for that. And then there is just, it uses Tokyo. I just use a Tokyo interval and run it every 7 seconds to generate my sample. Okay. So how does Rust help with vehicle streams? The service has evolved quite a lot. I first wrote this service about 4 years ago. And I initially wrote it in JavaScript where a small crash would just collapse the whole thing. I moved it to Kotlin in the JVM, hoping that it'll be better, but then I had to keep throwing more RAM at it. If you're at Rust Lab, you remember I talked about going from using 20 gigs of RAM to less than a gig of RAM at peak time. So it took a few months to rewrite it in Rust. This was actually when I was still learning how to use Rust. So this was about 14, 15 months ago. And I'm seeing very impressive performance. I previously talked about how the service just runs for months on end. I never need to restart or anything. I use a third of the CPU usage than before. I talked about the 20 gigs of RAM going down to around 500 megs of RAM. And the main benefit here is that I was able to replace an in-memory cache with a simple hash map. I'll talk a bit more about this. And then the service is easier to maintain and extend. And then there's a notification service because I mentioned that users have an Android app. So when one user is submitting samples, other users are relying on that sample. It's a Fire-based cloud messaging service. I recently found this Crate FCM. I think it was abandoned effectively, but somebody picked it up and started using it, which is also one of the nice things about open source in general. It notifies users based on a range of things. I've got an enum there that just shows the different types of alerts. So it's effectively a generic cloud messaging app where I can just keep on extending it by different types and then send them out. So it's not really train delay specific. We personalize the information for individual time delays. So if you've got 5 people waiting for the train at different stations, and you notify one user now, but the delay doesn't affect the other person. When it does affect the second user, you only notify them. So we sort of keep state of each individual user and when last we notified them. Because one of the things we try to avoid is spamming users by sending them 100 notifications per second, because immediately someone's just going to delete your uninstall your app, and then you're never going to see them again. Okay, and then the service also uses Actix, but instead of using gRPC, we use nets.io. So within the whole architecture, there's messages just being passed around quite a lot. I used to use Kafka, but now I moved it to net.io. A new subscription from users are added in real time. The nice thing with subscriptions is that a user says, I only take the 7 a.m. train, or I only take trains from 7 a.m. to 8 a.m. and between station 7 and station 24. So once the train passes station 24, we don't notify you about anything because it's no longer relevant information for you. This is also one of the nice things because the fast train service that I talked about, they will send you a notification about a bus in some faraway place not running, and it just irritates the poor user experience. All transit data state is loaded at startup when the application starts, and I keep it in memory. So static data like what the train numbers are, what the stop locations are, etc., and as well as the trip data. The benefit here is that we end up storing everything in memory because the application effectively, as long as the application doesn't crash, which is one of the benefits of Rust, it'll keep running indefinitely. So if you use Actor systems quite a lot, you'll know that some Actor systems support snapshotting where once periodically you'll save the user state onto a database so that the application crashes, you can recover that state. Here I sort of cheat because I don't use that. I just load everything in memory and keep it running from there. So why Rust then? The main benefits are that I'm really getting stability out of this because being able to write a program where I can prove to myself or to the compiler that it won't crash and I handle every state that could cause a panic helps me to create a cheap in-memory store using a hash map, for example, instead of bootstrapping Redis or Memcached or something else. So you'll notice that I don't really use Rust for something very novel per se, but it's really just to give me the stability and the performance. Actix has been very good to avoid concurrency issues, so it makes it easier to think about a lot of things. Interestingly, I rarely ever have problems with borrow check or lifetimes or everything because everything is quite simple effectively. The cost saving is the important element for me because this is a hobby and maintaining this means, well, if I was doing it as a profession or whatever, I'd have to wake up at 3 a.m. in the morning to notify users of cancellations of trips and all of those things, and then stay up all day until late at night. Because it's a hobby, it's very costly. Every hour that I spend on this is an hour that I could be working as a freelancer and putting food on the table, etc. And also the other thing that I save on a lot is server costs. Initially, about 2 years ago, before I started using Rust, I had to have a 64 gig server because the Kotlin service would use about 20 gigs of RAM, and then all the other services would cumulatively add up. So I used to normally run at about 40 gigs of RAM usage, just running this aspect of this public transit stuff. And now the services that I just talked about in Rust, including others that I haven't mentioned in this talk, I can run all of them in a 1 gigabyte container with 2 CPU cores. So that's significant for me. And then the other thing is scalability in terms of performance. Right now, talking that I use 2 CPU cores, I actually use very little. And if we were to expand the services, maybe even 10-fold or even 100-fold, I'd still be able to use them within the same resources. Okay, that's it from me. Are there any questions?
Oh, thanks for the interesting talk. By the way, I already saw you in the Rust Lab. That's amazing. About the scale of the thing, so how many users does this service actually serve concurrently? And what's the frequency of the notifications and messages to and from users, just to get an idea?
Okay. In terms of the number of users, we get about 100 users a day submitting samples. Then there's a lot more who receive samples. So it's not very frequent, and it's only really busy in the mornings when a lot of people are taking the trains, and then again throughout the day you'll see one sample once in a while, but it's not a lot. And then in terms of notifications that are sent, there's a hard rule that says that we won't send a notification to someone for the same train within 5 minutes, but we send about, I think the last time I checked it was about 400-500 notifications per hour at peak times. So it's still quite a young service.
Any other questions?
You, again, very interesting talk. You mentioned you run it from about 3 a.m. till late in the evening. Does that mean you can shut down your service? And if you didn't have that option, would you have to change anything about your infrastructure?
So in terms of running it, the running aspect of it is a warm body standing on a chair, looking at cancellations more than delays, the whole delay infrastructure is automated. It's the cancellations where there's a WhatsApp group from the train operator where they say this train has been cancelled, the train has been cancelled. So those ones we can't automate as yet. We have to capture a cancellation and send that out. Everything else is just automated. So at night when it's based on schedule, so if there's no scheduled trains that are running, the service will just keep calling every 7 seconds but do nothing. And then once activity picks up, it starts running. So it always runs 24/7.
Hi, great talk, by the way. I was just wondering, does the app send regular regular updates, or does the user have to actually send the update themselves, press a button or whatever?
Oh, my apologies. I actually didn't talk how users submit. So there's two ways that users do it. First one is average if a user's waiting for a train, about 3 trains will pass by, depending on where they are. In the main central stations, there'll be a lot more. So when a train passes by, you can spot the train by saying, I just saw train 1, 2, 3 passing by. And then we use that one-off sample to calculate. But then once you get on the train, similar to if you've used Waze, it's something similar, where once you get on the train, you can say, I'm on this train, and then it'll take a sample every, I think it's between 45 and 60 seconds. That's how we get the sample. And then once you get off the train, it stops submitting.
Thanks.
Very nice talk. So you mentioned you store the state as a hash map in memory. Have you ever had the issue that the state got too big and you were not able to forget? So something you get using Redis and Memcache is TTL, so you can forget an entry automatically. Do you need to handle that in your application, or is that not an issue?
So I use both. There's a trait called TTL index, I think, I can't remember. I use that for state where I want to keep stuff for a short life, specifically on the vehicle service. The reason why I use hash maps for the others is that it's static information that doesn't. So if I restart the application once a month, I'll just load that information and keep it in there month. I do incremental updates where there are changes that happen. And then in terms of the application getting big, so right now with about 7,000 services, 7,000 different routes, and 7,000 vehicles, I use less than a gig. So in the vehicle stream service, I use about 500 megs, and then in the first service, which keeps static information, I use about 400 megs. So if for example I were to increase the services by 10-fold, I'd still be able to handle it in, let's say, 10 gigs of RAM. So that's not a concern.
Do you have train spotters in South Africa? And could you maybe change your app a little bit so that it gamified it for train spotters?
Well, there's a lot of stuff I didn't talk about, and I see there's a lot of questions about it. So one of the things we do on the app is we keep track of how many we've created a point system for train spotters, where based on how much the train still has to travel, you'll get more points. And if there's no similar information, if you're the first person submitting that, you get more points. At the end of the month, because a lot of the people are often students, etc., we buy them data and small prizes that I can afford. It's out of pocket. And then the other one is we keep track of how many kilometers in total you've traveled. And we also incentivize those people. So we do gamify. Because otherwise, people don't see the benefit of spending their data helping sharing information, even though it helps.
More questions?
I don't see any. Do you know if the train drivers use the app as well, or are there any plans for like the company to use it?
Some background. One of the problems we have in our country is that the government outsources a lot of its services through a tender system. The problem with that is that even when you are coming with good intentions, trying to help out, they can't just take your services. They have to go through procurement processes and all of that. So that's one of the challenges. We have put in a proposal a number of times where we said, instead of putting GPSs on trains, because the trains are old anyway and they might get vandalized, let's create an app for train drivers, because all train drivers have smartphones. And then those drivers can, when they get on the train, they can say, I'm logging in on train 124. One of the problems, though, that we have, because we've tried that with buses also, is that bus drivers are very unionized, so there's a lot of organized labor, and there's always issues about whether this information will be used to the prejudice of drivers. So sometimes the drivers aren't very honest, in the sense that when a bus is supposed to leave at 9 a.m. or it leaves at 9 every 15 minutes, sometimes the drivers will intentionally not leave at 9 a.m. and leave in a bunch together. So if you know public transport theory, I think the concept is called bunching. So there's quite a lot of issues that work against us trying to implement that. But we are trying to get it done, because if we do that, then we don't need to process things.
Anyone else? Okay.
Thank you.
Thanks, Neville, for your talk. Next up, we have Niklas talking about web audio applications. Niklas is really deep into audio. He works in audio, and then in his free time, he does more audio. And part of that is sort of artistic live coding. And I think he's going to demo, so I'm really looking forward to that. And Niklas is a German, or is originally German, but actually lives in Barcelona, so it's a home game for him. Give a hand to Niklas.
Hello. Good morning.
Can I start early or?
Thanks for having me here. I'm Niklas. I'm working for Eurecat, the local research and development center of Catalonia. And my job is making audio software, nowadays still in C++. And I'm fairly new to Rust. Could very well relate to Claudia Saxer's talk yesterday. My journey was pretty similar in the first few months. And today I'm going to talk about web audio and how Rust can be used for that, but also a little bit why Rust might be a good option for audio software in general. So why would you want to put complex web audio or complex audio applications on the web in the first place? I'm part of a community that does music with code. I don't know, who does not know live coding here? Oh, everybody knows it, I'm surprised. Doing visuals on stage with small programming languages, with domain-specific languages. And one of the problems that this community has is that workshops often end up being installation workshops, and after 2 or 3 hours, people barely manage to install their things, which is kind of sad because the stuff is fairly easy to use and it's a lot of fun to use and it might be educational. A lot of people might get interested into programming, but if you need 2 days just to install, I don't know, Lisp, Pascal, whatever kind of weird environment people develop their languages on, that might discourage a lot of people. So if you can put stuff on the web, you don't have any installation efforts, it's pretty platform independent, you just need to load a website, you don't need a lot of computer literacy, and it may just lower the boundary for people to use your stuff and might make it more fun for more people. So I went on the journey to try to port my own stuff to the web, and I'm still fairly early in that process, but I was looking for the perfect web audio stack. So what are the requirements for audio software in general? You need a deterministic way of working for the audio thread itself. That means you shouldn't allocate memory in the audio thread. You shouldn't lock, you shouldn't wait on condition variables and all those kind of things. And audio software is inherently multi-threaded because you always have the audio, the real-time thread, and some control thread at least to either set parameters or schedule stuff, sequencing stuff, and so on and so on. And out of personal preference, what would be nice to have, not only for the web, but for audio software in general, memory safety is a big thing, because if once in your life you had the experience that you missed an array boundary and suddenly get random memory contents pumped directly into your ear, what at work we affectionately call noise from hell, then memory safety becomes very important suddenly, just to be able to keep on working and not being deaf. Portability is a thing, because like for me, like if at some point I would not be happy with the web performance anymore and want to have a native program, it would be nice if it would be easy to port, small footprint. I don't like bloaty software, and the easier it is to use, the better. So what were my options here? I could go with pure JavaScript, but it's it's not that portable. I'm not an expert in JavaScript, but I think compiling it to a native executable is something different. It's a dynamic scripting language. That means it has probably something like garbage collection, which in some languages can easily stop the audio for a second. You get glitches, and it gets easily bloaty. I don't want to chime into JavaScript bashing here. I like JavaScript, but I don't think it's the best for this kind of purpose. You could just compile C++ with mscripten, but that's neither very convenient nor very, comfortable. I don't know. But so I came across Rust and WebAssembly, and that seemed to be a fairly good option. Why? Well, so first of all, I looked around and tried to find something that has already been done, and I came across this little synthesizer that's not made by me, but by some person from Japan. And that was the proof of concept that showed me, okay, it's actually working. It's like a little TB303 simulation, kind of funny. Even though it was still lacking a couple of things like sample playback or precise timing and all kinds of things that still needed to be done. And apart from that, everything that's written about it is in Japanese, which is a beautiful language of which I have very little command, unfortunately. So I needed to put some effort into that. So yeah, why use Rust for audio applications in the first place, and for web audio applications in particular? So the memory aspect, the memory safety aspect, I already lost a few words about that, why you would want to have that in audio software. Rust boasts itself with fearless concurrency, so for multi-threading applications, it might actually be pretty good. It's a deterministic systems programming language. It gives you stable results. You don't have any garbage collection to deal with, and don't have to expect glitches. You can port it to the web, or if you're not happy with the web audio software anymore, you could easily compile it to a native executable. The WebAssembly integration is very seamless, like compared to C++ or other languages, where you have to struggle with mscripten or whatever. For Rust, you just set a different target, and there you go. And last but not least, the performance. I only did some very casual profiling in the developer console, but I had to, looking at the numbers, the main audio processing method needed roughly 15-20% less than the native JavaScript applications. I made an application to test sample playback and to work around, in general, get used to working in Rust and WebAssembly. This usually needs headphones, so it doesn't do a lot on a single mono speaker, but it's just a very simple sample player. And for profiling this stuff, I did the same thing in pure JavaScript, and it seems to be more reliable with Rust and WebAssembly. So, what are the ingredients of a web audio application made with Rust? Well, first of all, you need your DSP module that is compiled to a WebAssembly module. Like, BindGen doesn't really work that well in that context, so it's a raw library that you compile to WebAssembly. You need the audio worklet that holds the module. It's a part of the Web Audio API that allows you to do custom DSP processors, and that can use a WebAssembly module. You need some setup and control script, obviously the main thread, the user interaction. If you want to do any scheduling, any time-based stuff that's coming along, you need some additional web worker thread for sequencing and this kind of things. And ideally, some pure Rust DSP crates that easily compile to WebAssembly, as opposed to bindings, like if you want to use some advanced C Fourier transform libraries like FFTW or whatever. Well, it's probably harder, but with the pure Rust crates, that works pretty well. What are the challenges of making a web audio application with Rust? The audio worklet and web worker stuff is a little bit tricky because you cannot load the modules directly. You have to fetch them in the main thread and then post them using the message system. But once you got through that, once you got the setup done, it's fairly easy. Setting up the shared memory between the WebAssembly and the main JavaScript is a little bit tricky. And yeah, as I already said, it was the bindgen for the worklet part itself for the DSP module doesn't work all that well because because of the limitations of the audio worklet, that you cannot load a module directly in the worklet, that you have to post it there in binary data. What's already there and of crates that support or that help you creating audio software with Rust. There's CHFFT, a pure Rust Fourier transforms library, if you would want to do any convolutions, any FFT-based effects. I used that for the binauralization of this part, like for the simulation of the 3D impression in this, if you want to check this out with headphones and play around with it a bit. The current version is still time-based convolution, but the new version that I might upload soon is based on actual fast convolutions. There's an alternative called RustFFT, but I haven't had a lot of success with that. There's some basic DSP crate, which I wasn't super happy with because it's a very vector-based way of thinking, and well, that's a little bit too detailed maybe. But anyway, it exists, so you might want to check it out if you are into DSP and want to do some audio software with Rust. What's not working all that well yet? I haven't managed to do any threading directly from Rust, so in the sense that I want to spawn a thread to do scheduling tasks, to scheduling music events. So you still have to rely on the web workers, I think, unless somebody knows something more, and I'm willing to learn because, as I said, I'm still fairly new to that in the first place. Debugging is a bit tricky, as we already learned in the talk yesterday. It's you should test your DSP code well to make sure it runs, because to debug it directly in the WebAssembly part is fairly annoying. And unfortunately, the audio worklet is not yet available in Firefox. So so far it only works in Chrome and Opera, which is a bit sad, and I hope it will be implemented in a proper way in the future in Firefox as well. But we are not there yet. So what is to be done? Like, one of my future tasks in general is to do some general benchmarking, because I want to know how the Rust software on the web in particular, but also in general, compares to my C++ stuff, which I haven't done yet, especially regarding fast Fourier transforms, which is a central thing in my daily work. To do fast convolutions, great. To be able to do reverbs on the web and I don't know things, what other things. And in general, I'd hope maybe somebody will be inspired to do audio software and we can sharpen Rust profile as an audio language in general, so I can avoid in the future having random memory contents pumped into my ear directly, because as I already mentioned, that's not a very pleasant experience. So yeah. Some resources. There's a Rust audio forum on rustaudio.discourse.group. If you need any help or introductions into Rust Audio, the Rust Audio environment is actually bigger than you might think. I have mentioned some things like there's a VST crate that you can use to do plugins for digital audio workstations like Ableton and whatnot, which I haven't used so far, but I know it exists. So if you want to look for any resources, that's where you would go. This is for some examples, if you want to learn from that, especially with the WebAssembly part. There's this original seminal example that I already presented. It's all in Japanese. If you speak Japanese, there's a lot of stuff written about that. If not, I did the sample player I presented you right now. It's well commented, so it might be a nice starting point for your own applications if you want to check that. And last but not least, a more complex example that I made, and as you say in my native language, grau ist alle Theorie. I might give you a little demo of that to give you some impression what live coding means and what you can do with Rust and audio. So put the microphone away and give you a little impression of that. Thank you for listening. I don't know if there's time for questions or anything else. All of this is running in a web browser. It doesn't need any kind of server backend. You just need to load a web page, and there you go.
Hi. Amazing talk and demonstration. Thank you very much. Last time I checked for web audio in Firefox, I think there was a limitation of 256 milliseconds on latency. I don't know how it is now, but depending on which kind of applications, latency is very important. Do you know if this is changing, or? And also, which is the difference between our audio worklet and web audio, if there is a?
I would assume it's getting less and less. 250 milliseconds sounds quite a lot. I must admit, my own work is mostly based just on output, not on input. I don't do live processing where this would be very important. So, but I've seen applications that do guitar effects in a web page, and they're fast enough so that you can play it with the recent advances. Like this, I don't know if I could find it yet, but there's like guitar effects simulations that run on the browser with the Web Audio API that are at least fast enough to test them and not completely bring you out of the rhythm when you play guitar. So I assume that would be better now.
Hi, great talk, by the way.
Thank you.
In the RustFest playthrough, there was a sort of scripting language that you typed and it made the music.
Yes.
What is it? Do you want a parser for it?
No, that is just a very, very simple pattern parser. It's basically just a sequencer that I made to test it. It doesn't have big functionality. That's my next project, basically, to make an actual more complex language for the synthesizer to use it more productively, or to port, I don't know, my existing stuff to this kind of things, and maybe other stuff. There's a lot of nice live coding languages, so that's a future project.
Good luck.
Thank you.
Final question? Raise your hand.
I'm curious if it would be technically possible to do this kind of audio processing with the main web audio without audio worklet, and if you can explain why this needs audio worklet, maybe it would help motivate implementation in more browsers.
Well, there's always multiple ways to do things, but yeah. One of the reasons for me is, for example, that if the performance isn't enough, I can use it natively as well and in different contexts, which might not be that great with pure JavaScript. Of course, everything of that could be done in pure JavaScript or with different tech stacks, but I think the Web Audio API itself and the nodes it currently provides is not that flexible. For example, all the timing stuff you saw here is done in the Rust part, like precise time. The scheduler, the pattern language only gives out very coarse events, and they're like re-queued and re-ordered in the Rust part, and so on and so on. So I think the complexity might just be easier to handle if you have a systems programming language there instead of the basic Web Audio API facilities. But of course, I mean, that's all personal preference in part. So there's of course different ways to do it, and whatever suits your needs, you can use it.
Thank you, Niklas. Give him a warm applause. I just got notified that unfortunately with the recording there was a problem. So the audio was not captured. So if anyone has a recording of that awesome demo, please share it with us, and then we can maybe put it somewhere else as well. So we are very happy to have 2 consecutive talks at RustFest this year about the hottest Rust topic, async await. Speaking of which, did you guys know that async await got stabilized and that the next stable Rust compiler got released Thursday? So you can use async await in Rust stable right now. Woo! So I tried compiling async std, the standard library variant of async, with the stable compiler, and it just worked. So yay! So yeah, I would like to thank all the contributors of that and the Rust core team for that specifically. So our next speaker, Florian, already gave an address for the core team yesterday morning. He's also known as the CEO of Ferris Systems and Ascara. Florian is going to illustrate this brand new feature using one of my favorite web project, async, the async standard library. Take it away, Florian.
Okay, there we go. Yeah, so hello and welcome. This is a very special talk to me because that means I'm so out of organizing this conference that they're letting give me talks. So just as an illustration there. So who am I? I'm Florian. You can find me on Twitter and on GitHub. I own 2 companies, one that has nothing to do with programming languages and the other one that does just Rust. I do program Rust since 2013. I do train it since 2015. And since then, I am a team member. I've also formed a couple of community things. I'm part of the community team. I founded this conference. I founded another conference based on embedded subjects. So I've been active. Today, I'm going to present the async-rs async std project, which is, we thought about the name for a while, and we came up with 20 names until we figured out, yeah, we're gonna call it async std because that's what it is. It is a port of the Rust standard library into the async world. It takes the whole interface of libstd, everything that does I/O or anything that might be thread blocking, then puts it on top of an executor, and the rest of the interface is based on the futures-rs library, which is the abstract interface to working with futures. The futures trait that was stabilized within Rust is a very, very minimal one to allow libraries on top of it to write extensions to it. It really has the bare minimum interface of this is what a future is, and all the operations that you can do on top of them are provided by the futures-rs library. Async std is not new. It's the summary of 3 years of experience. The people that have kicked it off were, first of all, Stepan Glavina, who is also known as the maintainer of Crossbeam and used to work on Tokyo, and Joshua Wyatt, who works on Tide and Surf, and me joining early. It's now developed by a global team, so it is a community project with a lot of the development nowadays being done by community contributors. So why are we building async std? First of all, stability. We believe that the Rust async ecosystem has been in flux for far too long, and we don't want to iterate further. We want to collect the knowledge of the last 3 years and implement them in a library and give it to you in a stable fashion that you can rely on. Ergonomics. It should be easy and consistent to be used, and we figured out that the standard library interfaces aren't actually bad. So there has a lot of work has already been done around ergonomics, so we have adopted them instead of coming up with our own again. So again, not doing research. Should be accessible. It comes with a book and full API docs. So we have extensive API documentation. It fully integrates with the wider Rust ecosystem, mostly with futures-rs. So it uses futures-rs as its base interface. And speed. Speed should come out of the box, so all this shouldn't be slow. And we believe it's the best library to get started with async await. And I want to give a personal motivation to the first point. As a trainer, I found it quite interesting that over the last 2 years, I have seen more and more people not be interested in async Rust training, particularly to the point where last year people have said, can you just skip the async part? We're not going to use this for the next 3 years. This is too much in flux. So this is the state we're in, just to be clear. It has a couple of additional properties. It has a very small dependency tree. It is not overly generic, which means it compiles fast and does not expose you to an end application, or does not contribute to an end application that compiles from it. Let's talk about async. So this is a synchronous function. It takes a path, returns I/O results, it reads a file, and by opening it and then reading it into a buffer through the read trait. And we provide the capability of doing this, basically adding async std in front of it. The only difference is that you need to manually add the prelude, because the compiler doesn't do that for us. And then you put async on front of the function, and every operation here becomes an awaitable future operation. So file open will notify you once it's done, and then you can continue. And the same goes for reading. Yeah, and yesterday someone, particularly Pascal, met me here and said, well, yeah, we used it internally, and that really works that way. We took our sync code, put async on top of every standard import, and it worked. And this is intentional, because async std exports all types necessary for async programming, including some re-exports of standard library type. So if we're talking about I/O result here, that's the same I/O result as the standard library has. And why are we doing this? The standard library has the habit of, at some points, actually being subtly blocking. For example, standard path has blocking function, particular exists or metadata and all of these kinds of functions. So if ever there's a type within async std that is not in that is also in std, you should use the async. But talking more about what async functions represent. So this is a manual desugaring of what the async keyword does. It does a little more. For example, it activates the compiler mode in which you are allowed to use await within a function block. But the most important thing is it turns the return type of a function into impl future item and the result that we have stated there. That is, that also gives an interesting insight in what those functions do. They generate futures. They don't actually do work. We'll come back to what that means in a second. But what does the await mean? The await means at all of these points, there is an operation where this task has to wait for something to complete. So it will indicate actively, I have to wait, register interest in a certain event. In the first case, I want to open a file. Please tell me when you're done. And this is what await. The active indication that you're waiting. It's also called completion based. So await is the moment where you wait for something. If we call this function, we get a nice compiler warning, which is futures do nothing unless you await and call them. That's what I mean by async functions are generating futures. So the return type of this is a future that will open this file. So it kind of moves the thinking in the future. That's where the name comes from. You're asking for please set up my program so that it can now open this file and tell me when you're done. And what do you need to run them? Futures are run using a task, and that one's important. And there's multiple ways to get to a task. Those mostly differentiate in blocking, non-blocking, blocking in the background. I come to the exact semantics in a second. The important thing is multiple futures can run in the same task currently. Tasks themselves may run in parallel. This is depending on the execution strategy. I'll come back to that in a couple of slides. as a differentiation for this talk, this is a really, really rough definition, but concurrent means multiple processes run in a group, yielding to each other when they need to wait, usually called cooperative scheduling. So any of those operations will go until they need to wait for something again and then actively indicate, I'm waiting, someone else can run. While parallel means multiple of these things run next to each other, usually on multiple threads across multiple. And when we talk about blocking, in this case, blocking, sadly, as many IT terms is not sharply defined. For this case, for this presentation, when I say something blocks, it is blocking the thread that's currently on, which means if you have additional concurrent tasks on this thread, they will be blocked as well. And that is a huge problem, and this is something to avoid. And this is why we choose how to run our futures act. So this is the task block on interface in async STD. You will pretty often see that in examples for the reason, that you need to block the main thread, as the same goes for any kind of example that does threading. You need to block the main thread to make sure that your program doesn't exit while something runs in the background. So all examples pretty often use task block on, because the definition of task block on is it blocks the thread you're currently on and instead runs the task that you are passing. So in this case, for example, reading the file. The nice thing about block on is it actually gives you the results back like if you had called a normal function. Because you can do that, you're waiting, you're completely blocking the thread until it's done, and then you can collect the results and immediately put it into a variable. The second interface is spawn. Spawn runs a background task concurrently and waits for its completion. It doesn't wait for its completion. It gives you a join handle back, and block on, you can then call block on the join handle, blocking the main thread. The semantics here are spawn spawns the future that does the operation, and it gives you a join handle back, exactly like the threading API in the normal standard library. Gives you a join handle back that is in itself a future, and the operation that this future represents is wait for the background task and then take the result back. So these are two different kinds of operations. It's always important to understand what is the thing that I'm actually waiting for. In this case, first of all, I'm waiting for the file to be read. Second, I'm waiting for the background task to complete. Join handles, much like the join handles in the standard library, will give you the result back that the task result. Join handles are similar to standard thread join handles. They're allocated together with the task that they spawn in one go. This is a single allocation, and they also provide you a back channel to the spawner, and the join handle resolves for them. There's a second function, and I mixed up my slides. This should be spawn blocking up there. There's a second function called spawn blocking. The body is correct. This is the old standard lib API. So this does blocking I/O, opening a file, and the way the standard library works is it will block the current thread until the file is opened, until the kernel wakes up that thread again. But spawn blocking indicates to the runtime, by the way, I am aware that there's blocking tasks, there's blocking things in this task, which will make the runtime put the task on a single thread, on its own thread, to avoid blocking other concurrent tasks. It behaves exactly the same. It gives you a join handle back. So what's possible, for example, is having blocking and non-blocking tasks resulting in the same time of result, mixing them, for example, putting them all in a vector and waiting for all of them. So our model unifies these things on the level of the caller, or on the level of the spawn. There's two patterns on futures that I would like to introduce you to, which are important. The first one being racing, the second being joining. What does racing mean? Racing means I take two operations and I wait for the first to complete. As an example here, I use the surf HTTP client, and I'm trying to get the index of two mirrors, for example, and I want to check out which one answers fastest. what I can do then is I can say, take the first future, race with the second, await, and I will get the first result back, and the second will be dropped and will be removed, and potentially the request aborted. So this is racing. Sometimes in the futures, crate, there's also a macro called select, which will have similar behavior, but not quite. But you may have seen that one. What's important here is, when we're talking about concurrency versus parallelism, these two are concurrent because I'm taking two of these, I'm putting them on a concurrent, I'm merging them into the same future, and then I'm running them both and on the same task. What I can also do is I can spawn both of them, which may run them in parallel because now the runtime is free to do so, and then race for the completion of the task. So this means I will, the spawner will say, let's join the join handles together and wait for one of them to return. So this is a similar kind of execution behavior, a different kind of execution behavior. The last pattern that I would like to present is joining. Joining is important in the sense of I have two operations and I want to execute them both, and I don't want to continue until they are both complete. So in this case, I want to make multiple requests to a backend and I want to wait until they are complete. The next concept I need to talk about is streams. Streams are a fundamental abstraction around items arriving concurrently into any kind of part of my program. In async std, they take the place of the iterator trait. So basically, standard iter is replaced by async std stream. So they can be split, merged, iterated over, all these kind of things. The classic example that you will probably have seen if you have ever had a look at async code is, and also even at sync network code, is the TCP listener. So the concurrent component of this is new connections are arriving to my program. I don't know when, I don't know how many, and I don't know how many at once. And streams give you the ability to work on this one by one. So the TCP listener on the standard lib has a sync incoming iterator. We have a sync incoming stream. And in now Rust 139, the recommended way of iterating over that is calling incoming next, stream.next. This is a future because we don't know if there's something there yet or it might come in the future. So this will lay the task sleeping until something is coming in, and we're waiting for it, and we're matching on it using the while let syntax. There's no integration into for loops currently in the language, so while let sum is your pattern to use. And then we spawn, for each of those connections, we spawn a concurrent task that works on them. Process is some function that processes this. And one important operation on streams is merging them. There's a couple of other operations, but I could give a whole talk on over streams on streams. Here's an example that listens both on a IPv4 and an IPv6 interface. So I can use two TCP listeners, bind them, get the incoming stream for both, and then I say IPv4 merge to IPv6, and then just continue. Because they are returning exactly the same things. They're giving me a TCP socket with a TCP connection, so I can merge them and then start iterating over them. We have a sync module exactly like standard sync. Comes with async await ready versions of standard lib structures. It is important to understand that a lot of standard lib structures, if they put you waiting, like for example, you're trying to lock a mutex, they will lock the current thread. So what our port gives you is they will lay the current task waiting. So it comes with mutex, barrier, read-write locks, all that. The classic. This is what the code looks like. This looks almost exactly like the standard mutex example that you have. If you look at the middle line, the difference here is the .lock.await. So if I can't get access to the mutex currently, lay my task sleeping, let other concurrent tasks run, and wake me up when it's my go. So it is important to use future-aware data structures in future code. One interesting thing is we have the ARC here. This is just an export from the standard library to make sure that you don't have a mix of STD and async STD types. Almost all types that async STD exports are either exported because they have a relationship to another one, or because we need to make changes. ARC is the small exception, and we don't want people to be too confused by having these small exceptions of maybe 1%, 2% of the interface. That becomes. We have a channel implementation. Async STD channels are based on cross-beam channels, but in an async version. There are multiple producer, multiple consumer channels. They're always bounded. We think that unbounded channels are an anti-pattern. You will run into problems with unbounded channel at some point, and then you're switching to bounded channels anyways. What that means is they can only, bounded channels can only hold a certain number of items at once. Otherwise, trying to write into them will lay your task sleeping. And they're very fast. They're faster than cross-beam channels. Cross-beam channels are the ones that are used in Servo in the browser end. Because they're multiple producer, multiple consumer channels, they should cover all your generic use cases. So that also means they cover one-to-one, they cover one-to-multiple, they cover multiple-to-one, just by virtue of covering end-to-end. Channels are currently unstable for API discussions. We want to fix that in the next couple of weeks, so you need to activate the unstable feature flag if you want to play around with them. Just as a short example, they work much like the stuff that I introduced. Specifically, the receiving end of a channel is a stream, so it can generically be seen as a stream, so the while let sum pattern applies. If you send, sending becomes a future operation, because if the channel is full, you will have to wait until the channel has capacity. And this is a ping pong example of two tasks or two futures that will ping pong each other through a channel or through two channels. And you spawn both of them, and they will start playing ping pong until Kingdom Come. Understanding tasks and streams, in my opinion, is far more important than understanding futures, because streams, channels, and tasks are the things. Tasks are the things that communicate. Streams and channels, streams being the abstract version of channels. Not everything, almost all channels are streams. Not every stream is a channel. Those are the things how tasks communicate. So this is, if you have the problem, how do I get some piece of data from A to B between two concurrent tasks? The answer is almost always use a channel. And so even if you're talking about, I want to work on a futures-based system, it is important that you have that in mind. So as a summary, async STD provides a known and familiar interface, the known and familiar interface of the Rust standard library with appropriate changes for async. It avoids pitfalls by providing a full API surface around all async critical modules. It is fully based on Futures RS, so it integrates into the ecosystem very well. We fully embrace the Futures RS library. So if you want to use async STD in an abstract fashion without relying on async STD types, you can take a step up and rely on the Futures RS interface traits, because all types expose the relevant interfaces from Futures RS. So futures, obviously futures, but async STD streams are always also futures streams, and everything that is read-write, async read-write is also futures async read-write. If you want to have the full interface of Futures RS, then you can also, on top of that, load the Futures RS library. One note about the Futures RS library: it has recently been re-architected to a core and a util and a couple of additions. And from core to util to some of the more remote additions, it becomes more and more experimental. So when I say we export the Futures RS library, Specifically, we rely on the core types where we know that they're going to be stable and and probably not subject to churn. But if you want to opt into any of the more experimental types, you can totally do so by just loading the futures.rs library on top and using it. Particularly of interest are the async read, async write, async seek traits. A lot of the criticism that we got is you're not compatible with the ecosystem, particularly Tokyo. The problem there is a lot of libraries are written on top of Tokyo, which don't implement the futures async read, write, seek traits unless you use a compatibility interface. They use Tokyo IO async read, write, seek, which are different and also subject to change, making them incompatible with the rest of the ecosystem. I think it's okay. Their view on this is we still want to experiment on this, and we would like to iterate on that interface, but that very much collides with our view that we should get stuff stabilized and that we have researched those traits for 3 years. So addressing the common question why async stid, it's pretty simple, fundamental mission goal. That's as deep. Our view and vision for using STD is applications should use async STD directly because application development is far less abstract. You want to pick a couple of libraries solving your needs, use them, and then the abstraction level is usually pretty low. You want to get stuff done. Libraries should use futures.rs as their interface. As an example, we have a TLS library under our own organization, async.rs/async-TLS, and this one operates completely on top of async read, async write. So it has no direct relationship to async STD, except that you can use it on all async STD, TCP socket, and so on and so forth types that expose read and write. So to make this more concrete, if you're in an application, it is okay to take an async STD net TCP socket directly. If you are in a library, I would highly recommend you to instead use futures IO async read. So that doesn't expose users to your choice of base runtime. Because there are other runtimes around, and this is something, there's currently a binary discussion happening around async STD versus Tokyo. I don't want to have this discussion because there's a number of additional executors in our ecosystem. Particularly Google Fuchsia is a very big one for the Fuchsia ecosystem. There's Bastion RS, which has a very different goal than async STD, which is this thing never crashes under no conditions. There's Wasm BindGen Futures, which is a particularly built executor for Wasm. And there's a number of company internal ones that those companies sometimes speak about, but pretty rarely speak about in public. And async STD is meant for writing compatible libraries. So if you're writing a library, you can use async STD as your test bed. Probably you should avoid binding to it directly. Which brings me to speed. That has been something we've been asked about a lot. There's a problem there. We also believe that there's a hyper-focus on benchmarks in the Rust community at the cost of ergonomics and barring stabilization. The biggest problem with benchmarks is they're often changing. We don't really want to be part of the benchmark race. So probably I'll present these benchmarks, and in 2 weeks they will look very, very different. And I also don't believe that you should choose software by benchmarks alone, which doesn't mean they don't factor into play. Still, on file reading, async std is 1.6 times faster than Tokyo. That was done by Jay Brosen. You can have a look at that benchmark repository. So that's only on reading a 256K file. If your application has a different read-write behavior, your benchmarks might be different. That's a fair warning. Our mutexes are fast. There's a fastest at creation, up to 9 times faster than the ones from Futures Lock Mutex. There's multiple interesting Mutex implementations. There's also a very nice crate called Futures Intrusive, which also gives you a lot of the base types that we export. So we are roughly twice as fast as Futures Intrusive and 9 times as fast as the Futures implementation at that. This also gives an interesting insight of, should I use Futures Lock Mutex? These types are mostly implemented for making sure that people can use them and run with them. So these were for the experimentation phase of Futures, and they're still shipped so that people that are rely on them can still use them. They are good. They are just not built towards they should be fast. So this is mutexes under contention. So actually mutexes that where there's frequent locking. There, we're up to 2 times faster than the fastest one, and we're the fastest one under contention. Mutexes without contention, and that is interesting, also have a speed cost. So mutexes that are rarely actually challenged. And there we're around roughly the same speed. Why do I say the same speed? When we run those benchmarks, they're highly variant. In the sense, the results will remain clear. Like the implementations don't change spot, but on the other hand, some of those numbers change up and down. And finally, how fast is task spawning? These are the Tokyo 10 times benchmarks. We're as fast and up to 2 times fast. There's another benchmark where we're slower, which is the channel ring benchmark, which is the classic Erlang benchmark that tests single-threaded executors, where you put up a number of nodes and connect them in a ring, and then you send a message around as fast as possible, multiple times. And there we're 0.9 times slower than Tokyo and roughly 3 times faster than Hack. So, yeah, notice, for the risk of side effects of synthetic benchmarks, please consult your local Apple keynoter. Conclusion, async STD is a fast economic futures OS-based layer for asynchronous applications. It is an innovative space. I want to mention that again. Join handles were built in async STD and then adopted by others. Single allocation tasks were invented or implemented first in async STD and adopted by others. You can both innovate and commit to stability. Be aware what you, which strategy you use. Our roadmap is our 1.0 will be released on Monday, so tomorrow, which will be a stable release with all base functionality and runtime concerns. Ongoing is stabilization of currently unstable library API, most importantly channels. Also, designing features that make async STD usable without the runtime. I think this is particularly interesting. What if I want all those features, but I actually don't want the runtime? We want to provide additional libraries with similar guarantees, ecosystem compatibility, one onus, interface stability. And just to be clear, there's a clear bet that we're going to have a 2.0 at some point. Because there's new language features arriving, and some of those might lead to breaking interface changes, not only in base grades, but for example, there is an asynchronous for loop coming, and that might need some interface changes to integrate well with that. And when these changes are coming down the line, we will release a 2.0 plus update guides on how to do that appropriately. And we would like you to hack with us on the next 2 days. So getting started writing more libraries on top or porting libraries to work with multiple executors. We want you to challenge our benchmarks because all benchmarks are wrong, and let's figure out how. If you want, we can get started writing an application, and we would like to get a lot of feedback on our unstable API because we want to stabilize, and that means we need a couple of eyeballs. Finally, async STD is currently completely funded by her systems, and we have started offsetting for all those projects. We are also hosting, for example, Rust Analyzer, an open collective. So if you agree with all those goals and would like to give us some more time to work on it, here's a funding drive. Thank you.
Thank you, Florian. We have time for 2 questions. Hands, please.
Hello, thank you for the talk. It was a great talk. Do you think there are ever any use cases in which Tokyo should be preferred to async standard?
Sure. No, seriously. There's at least 6 executors that I know of around. All of them with different tuning settings, different kinds of APIs. Yes, there's reasons for all of them. Tokyo currently has a better API for fine-grained control of placing of a runtime, which is a very, very detailed thing to do and needs a lot of knowledge on how to actually place runtimes correctly. And this is something that we currently don't provide at all. So yes, definitely.
You mentioned that racing and selecting aren't quite the same thing. Could you elaborate on that?
So the select macro of the futures crate is a pretty big beast that works on top of a library called proc macro hack, which implements by itself a way of doing, basically implements its own match statement along with 2 different kinds of operations to how to react to an event happening on each of the sites, on each of the branches. So what I was hinting at is this select in Rust isn't a very well-defined term, while racing is pretty clearly there's 2 futures giving you the same results. And that's also the other thing. The select macro in the futures crate allows you to use 2 futures that return different kinds of results and react differently on whether the one resolves or the other one resolves. While racing is, I expect the same back and I wait for the first. So it's a vastly simpler operation.
Thank you, Florian. So we're heading to our coffee break, but before that I have a few announcements again. So yesterday I told you something about the glass containers. Apparently still some glass containers were thrown in the bins yesterday. There might also be glass in like your lunch bags for when we go to lunch. We do not go to lunch now, but when we do, there might be glass there as well. Please leave those in, leave them on the tables as well when you find them. Do not throw away the glass. When you leave this auditorium, if you have any rubbish, please also take that with you and throw it outside away, so that we do not have to go through everything and clean it up again. Also, remember to hydrate yourself. Please drink enough water during the coffee break, so do not only drink coffee. And finally, could the next speakers, Tylo, Pietro, and Katerina, go to the stage so that we can do the technical setup before we continue? So go to the coffee and have a nice drink, have a snack, and we'll be back here at 11:30.
Do you have a? Yeah, I have a download. Do you have another? I don't know if there's people that like they're in the. I don't know if they need to manually switch, right? They do.
Dear tech team, please switch to the speakers for tech setup. Thank you.
I hope it works. You should recognize that. I don't know if it works. Do you have a clicker for to the slides? Oh, okay.
You have you have also this stuff. I don't know if it works.
I don't think you don't see it from.
Yeah, you don't see it. No. I don't know if you're gonna need that anyway, but
No. Maybe probably for.
another cool feature this have. I don't know if it's timer.
Yeah, like I have timer somewhere. Like I hope this works. Like.
Yeah, most likely. We're streaming 1080p.
Yeah. Yeah, like I need to. Like yeah, because it's actually something I wrote like 4 years ago. This thing in JavaScript to actually do present the stuff for with PDFs. Like yeah, but actually full screen and such.
Are they switching now?
Can you switch?
So this microphone has buttons.
What the hell is happening? Like what? Okay. No? Yeah. Yes. Yeah. There was Tyler and someone else.
Tyler Mandry, please come to the stage. I've seen an adapter for that. That's USB-C.
Okay. This is the mic, or?
No. Well, yes, but you have to stay like this.
Okay.
Just use this. Switch.
Okay. Hello. Close. Okay. All right.
The risk with this one is when you start talking and you
Yes, I
fade away.
normally I have like a
Yeah,
thing, but
it's broken. We tried the first talk with it.
Okay.
Cut out the audio all the
okay.
So Yeah, this is the backup. So in
Okay.
case you forget, hopefully this will pick up
Yep.
something.
Cool.
And we can maybe rescue it. But who knows?
The last conference I was speaking at, the boom mic was kind of dodgy, and so I was asked to put my phone on the thing as well and like record, just so because like the it was like two audio systems, right? One for the actual hall and then one for the recording.
Yes.
And so that they had like a backup source for if the boom mic was just shitty.
Yeah.
That I sent them my phone audio to sort of
Synchronize.
yeah.
Yeah, it's weird stuff. That's it. You will be sitting there with the controller.
Nice. Already. Yay! Thank you. Cool. Yeah. Wow. Linux does display. Damn. What's going on? Uh.
Yes, but there's also for all your Mac. Have this little screen over there.
Ah. Oh, there we go. Wait, what? There we go.
There you go.
Then, yay, okay, that works. Cool. All right.
Okay. We'll do that.
Yeah. I'll leave my charger here, just so that it's already hooked up and everything.
Yeah, we have 5 minutes planned. So this is the backup microphone.
Yeah.
So this only works when you speak here, right?
Mhm.
You have to be here.
I see. Okay.
For everything else, we use this one. The switch is here.
Okay.
Just keep it up here, because
Yes.
when you start fading away
I know.
around here, it gets wacky.
I'm worried I'll do that.
Yeah.
Someone had like a little headset thing.
Yeah,
Was that
sadly,
their own?
that's broken.
Oh.
We
Awesome.
used it, but there's an audio filter somewhere that comes out every other
Oh,
second.
that's annoying.
So people said, hey, we don't understand anything. We have to read it. So
Okay. All right.
it's very strange.
That's fine.
It works with service.
I see.
We'd rather not use it.
Yeah. Okay, so I can kind of hear it here, but then like back here, there's very little.
Yeah. This
Okay.
is the backup. With post processing, we might be able to get
Right.
some audio out.
Okay. Great. Okay.
You
Cool.
want to use the click?
Yeah. Yeah. Okay. Can't see my mouse. There it is. Actually. Windows. Laggy. Okay. Cool. So good.
Dear tech team, we are about to switch back to the timetable.
Cool. Okay, great. Okay, and then you said the clicker is plugged in, so I should. Okay. Oh, yeah. I think I saw the screen come up. Yeah, it's working. Cool. Alright.
We'll switch back.
Yeah, that's good.
We'll switch back to the table, and once.
Okay, cool. Here.
Sure, if you're going to do it slowly, the camera will follow you.
I see. Okay.
If you stay here.
Yeah, I might be tempted to walk around a little bit.
Yeah, yeah.
Oh, do I? Thank you. Okay, it should be
You can
off.
disable it. It's fine.
Yeah, I don't.
Probably with the color.
Yeah, I don't think it's like explicitly on anymore, but does it look that way? Does it look yellow? What now? What now?
Color.
Does it look better?
Still on. Probably not.
I mean, I don't have like flux or anything. All I have is night shift, which is completely disabled. Only on this one. On this. Yeah. Does that work? Okay.
But it's on now. So
Well,
turn it
it's
to more warm.
like if I let it go, then it just turns all the way back off.
Yeah, I don't know. We'll leave it as is.
Okay, so but this color profile works the best.
It's very blue. Yeah.
Very blue. Okay.
Yeah. The little yellowish.
Yeah.
But I mean, you can try. Lighter. And this is. Yeah. Let's stick with that. Okay.
All right. Cool.
So we are. 11:30.
Yeah.
So still 5 minutes.
Cool.
You want?
Oh no, I'm good. Said 5 minutes ago. Might more water. Oh, should I stand up here or just?
On the.
Okay.
Everyone, please sit down. We're about to get started.
Welcome back, everyone. Please take your seats. Don't forget to move inwards and compress yourself. We'll start within 1 minute.
All right. So next up, we have another talk about async stuff. And this is a talk from Tyler. And Tyler works at Google on Fuchsia. So you can imagine he might be really deep into async stuff. And I also noticed that he wrote some pretty cool blog posts about how he optimized the functionality or how async await functions work in the compiler. So if you're interested in, you might want to check out his blog as well. But let's first see the talk, because maybe he will explain more about it. I'm excited already. Give him a hand.
Well, in case you haven't been paying any attention, async await is now stable in Rust. This is a huge milestone for the language and I think systems development in general. So very exciting. Again, my name's Tyler, or Team Andrew. I work on Fuchsia, which is an experimental operating system at Google. We use Rust for a number of things in the operating system. I work on the toolchain team supporting Rust, which means that sometimes I get to spend time fiddling around in the compiler. And I'm also a Rust release team member and compiler team contributor. So I just want to briefly give kind of a primer on futures before I dive into some of the async stuff. Florian covered some of this, so just to recap, a future is any computation that progresses asynchronously. So that could be like a request to some external database server. Could be like reading and writing to disk, or doing some expensive data processing on another thread, something like that. All of these things can be represented with a future. It eventually produces a result, which is called its output. And we represent futures in Rust with a future trait. So you can see there's an associated type called output, which is the output of your computation. And then there's this method called poll, which has kind of this scary signature. But the job of the poll method is to make progress on the future, as much progress as possible. Poll returns an enum called poll. And basically the result of the poll method is always either pending, which means that I've made as much progress as I can, and now I'm waiting for some external event, or ready, which just means that I'm completely done, and here's the result of my computation. And the important thing to remember is that in Rust we have a lazy futures model. So futures don't do anything until they're polled. And it's the job of the executor to do that. Okay, so I want to talk about async functions in this talk. And I'm going to start with a really simple example of an async function. So here's an async function named handle request. We're going to take some arguments. The first thing we're going to do is we're going to issue a request to an external database server to get a row from our database corresponding to the ID we were handed. We're going to await the result of that. So basically suspend execution of this function until we get the row back. Once we get it back, we're going to encode it into JSON. And then finally, we're going to write the encoded JSON out onto a TCP stream. Now, if you're coding this synchronously, your function would block your thread at two potential points. One is when you're basically awaiting the database server, and the other is when you're writing out to a TCP stream, because TCP sockets on many platforms have a buffer that can fill up, and if the buffer fills up, you'll block your entire thread, and at minimum, you'll pay a context switch, or your thread could be locked for a really long time. So the way this connects to future, as Florian mentioned earlier, is we rewrite the signature in the compiler of your async function to just be a normal function that returns impl future. And that means that we are returning some type. We're not going to tell you what type it is that happens to implement the future trait. In this case, our async function did not have a return type, so the output is just the empty tuple type. And then inside of the function body, we just wrap it with an async block. So let's talk about what the compiler actually does when you compile this async function. And to do that, I want to walk through how you would implement this by hand in the pre-async await world. So the way you would do that is you want to create a data structure that represents the state of your request. And so we're going to do that. We're going to call it request handler, and to start, we'll just stick all the arguments to our function into that struct. And then we're going to implement future on that request handler. Again, our async function doesn't return anything, so the output associated type is just empty tuple. And then we're going to implement the pull method. So the way you implement this by hand is by writing a state machine, which is what we're going to do. We're going to add a state field to our struct that just keeps track of what state our request is in. And then inside the pull method, every time we get pulled, we're going to match on that state and basically behave accordingly. So the very first state that we can be in is we've never been pulled before. This corresponds to the very top of the async function. The next one is that we're getting the row, so we're waiting the result of the database. The third is that we're writing to our TCP stream. Notice I didn't create a state for encoding the JSON. That's because that's a synchronous operation. There's no await. And then finally, we're completely done and ready to return our result. So let's go back and actually fill in the. So in the case where we've never been pulled before, we're going to just basically execute the very first line in our function. So we're going to call getRow, and it's going to return a future, which we're going to store in a field of our struct. Then we'll update our state to getting row. So like I said, getRow returns a future. We're going to store that in a field called rowfut. And we use an option here because when we initialize our data structure, we have to initialize all the fields. So we need to be able to say, I don't have the rowfut yet, there's none. And then when we do have it, we'll initialize it to sum the value of the future. Then once we're called, we're pulled when we're in the getting row state, we're awaiting some subfuture, right? So we need to propagate this call to pull down to the future that we're awaiting, right? So we'll do that. We know there's a future inside of rowfut because we're in the getting row state. We call pull on it. If that call to pull returns pending, that means that we can't make any more progress in our function because we're awaiting some other future, and it can't make any more progress. So we just simply propagate that back up the stack. If we get poll ready, that means, okay, the row's ready, and so we can make progress. So the very first thing we do is we can deallocate the row future. We don't need that anymore. And then we're going to do the next thing in the function, which is to encode our row into JSON. And then we do the next thing, which is to create the write all future. So we call write all. Again, we're going to store the value of that future in our state machine. And then we're going to update our state to be writing. All right, so the next state is writing. This one's really simple, basically the same thing that we saw before. We're now awaiting the write fute, so we're going to propagate our call to poll down to the write fute. Again, if it's pending, we'll return poll pending. If it's ready, there's no output of the write future, so we just immediately update our state to be ready, and that's it. The ready state is really simple. You just simply return. Right? So there's one last thing that we need to do, which is add a loop around the inside of our body. And that means that every time poll gets called, we make as much progress as we possibly can until we either hit a poll pending on like a subfuture or we're completely done. So basically, we will constantly loop until we hit one of these 3 return statements in the body. So you notice there's quite a bit more code on the right side than the left. It's not as readable. And so that's one major benefit of async await, of course. And in fact, we actually cheated and actually made the code a little bit more readable than it would have to be in real life, because we're actually we're borrowing one of our struct members with self.encoded inside of the value of the write future. So when we call write all, we're handing it a reference to basically the encoded buffer. And you can't actually write this in normal Rust. You'd have to introduce a layer of indirection with like a smart pointer or something. And it ends up being like really not fun. And this is an issue that comes up a lot in async. But thankfully, with async await, all of that is taken care of for you, and it's more efficient. The compiler just says, okay, I know that you are borrowing yourself, and thanks to some abstractions like pinning, we can guarantee that this is safe. Another problem with our hand implementation that you might notice is we're actually wasting some space here. Anytime we're like in the middle of getting the row, we don't have any need for the write fute, encoded bytes, and then in the next stage when we're writing to the TCP stream, we don't need the row fute anymore. So it would be really nice if we could not allocate all of that space and just kind of reuse the bytes. If we look at the way that it's laid out in memory right now, we've got like byte offset 0 of our structs, and you have all of the fields. So this is the way it is now. What we'd really like to be able to do is basically, again, reuse those same bytes from row fute in the next stage when we're awaiting the write future. So as recently as a few months ago, the compiler didn't do this, and this problem actually compounds really quickly. So if we assume, for simplicity's sake, that the size of our future is basically dominated by the size of all the subfutures, then we're roughly twice as big as we need, not reusing those bytes. And that's a problem, but it actually gets worse because, well, row fute and write fute, those are written as async functions, and those each have their own problems where they're awaiting different subfutures, and so really those are twice as big as they need to be. So really the future we're writing isn't twice as big as it needs to be, it's really 4 times as big as it needs to be. And then if that gets awaited by some other future, then maybe that's like 8 times as big as it needs to be. This really did happen in practice. So in Fuchsia, we would have futures that took up like 0.5 megabyte on the stack, which is just really big. And well, we had a lot of futures that actually blew the stack, and you can actually segfault in Rust if you go past the end of your stack. It's not undefined behavior, but you can segfault. So what the compiler wants to do is it wants to ask the question, okay, well, which of these fields can I overlap? And the way it does that is it looks at the control flow graph of your program. I'm going to zoom in here so you can actually read some things. So this is kind of a graphical representation of what's called mirror, or the mid-level IR inside of the Rust compiler. We represent the entire program as this control flow graph, where inside of every block, these are called basic blocks. So like on the left side in the middle, you'll see basic block number 14. And inside of that block, there's a bunch of statements. These are very, very simple statements where you can only do things like, oh, I would need to allocate storage on the stack for like a local variable, or I need to access one member of this variable, or dereference something, or assign something. There's no control flow inside of the basic blocks. All the control flow happens between the basic blocks along these edges here. So at the end of basic block 14, we drop something. And drop is an operation which can panic. So there are two options. Either we return and go down the happy path, which is normally what you think about, down to basic block 23, or we panic and we unwind, going to basic block 7 to do all of the cleanup in the case of panic. So what we're going to do is we're going to draw this entire control flow graph and figure out which variables are storage live at the same time. Storage live is how we represent that we actually need storage for a variable. We're not actually going to do that because we don't have 3 hours for this talk. So we're just going to squint at the source and see if we can figure anything out. You can do this at home. It works pretty well. So the first question we're going to ask is, okay, can I overlap rofute with encoded? And the rule of thumb here is, if the last time you ever use a feature is, the last time you ever use field A happens before the first time you ever use field B, then you can definitely overlap those. So in this case, you'll notice the last time we use rofute is we set it equal to none, and then the following line is the first time we ever use encoded. And you can kind of reason about this by looking at the source and say, okay, definitely these are never needed at the same time. So yes, we can overlap these in memory. When I say overlap, I mean just reuse the bytes, right? Okay, so what about rofute with writefute? Again, in this case, rofute, the last time we ever use it is setting it equal to none, and then later on we use writefute. And so we can definitely overlap these two. And then the last two fields that we care about are writefute and encoded. So in this case, we assign to encoded, and then we assign to writefute, and we're actually handing out a reference to the encoded bytes, which means that we definitely need these at the same time. Writefute actually contains a reference to encoded, so we can't overlap these in memory. And so what this allows us to do is exactly what we said we wanted to do. We can actually just overlap these bytes. So what this ends up looking like is not so much a struct, but more like an enum, where you have one variant for every state your future could be in. And inside of each enum variant, you have all the fields that you need for that particular state. So in general, in this table, we have like all of the enum variants. So we could be an unpulled state, suspend 0, 1, 2, etc. And then all of like our local fields on the left here. The only difference between a regular Rust enum and this is that you can have one field and multiple variants. So like in this example, we need local A starting in the suspend 0 variant, but then also need it in the suspend 1 variant. And so you can have one local that persists across multiple await points, right? That comes up quite a lot. So I want to talk about, this is all very cool, but what are the performance implications? So let's look at some patterns that you might not realize have like subtle performance issues. So in this example, we have a function called doStuff. We take a context, which is just a smart pointer to some context somewhere, and what we're going to do is we're going to log some debug info with the context. Then we're going to call some other async function foo and await it. There's a subtle performance issue with this code. Can anyone spot it? Nod if you think you see it. Not seeing any nodding. Okay. So, so what can happen is, at the end of every scope is when we drop our local variables, right? So the compiler is going to insert an implicit drop at the very end of our function, but we don't actually need context until the end of the function. We just log it at the very beginning. Right? And so we're actually hanging on to this smart pointer to context all the way through awaiting that original that future and then finishing the task, which is kind of inefficient. If we have the only reference to context, then we'll be keeping that memory around. We don't need to be. So what we're going to do is, one way to mitigate this is to move that context into basically an inner scope in the function. And the effect of this is that we're actually moving the drop until the end of that inner scope before the await. And this is quite a bit better. We're not hanging on to context while we're awaiting some other future. That future could take a year to complete. We have no idea. But it's still not perfect. And the reason for that is, remember, futures do nothing until they're polled. And in the case of an async function, that includes all of the lines at the top of the function. So none of these lines will run until the first time poll is called, which means that we're still hanging on to context while we're in that unresumed state. So the quote-unquote perfect way of dealing with this is to actually desugar our async function into a regular function called doStuff, which returns impl future, like we saw earlier. Compiler does this for you, but you can do it yourself. And at the very top of that function, we'll do our log, and then we'll write an async block, which drops us into an async context where we can await anything we want and actually evaluates to a future that we return. And because we don't reference context inside of the async block at all, we never have to save it inside of our state machine. So we aren't allocating any bytes to save the smart pointer, and also never hanging on to that reference inside of the future. So once doStuff is called, we just immediately log, and then we return a future that can make progress later. So another pattern to look out for is when you're awaiting expressions that have really big, complicated temporaries. So in this example, I have a struct big, which has an array in it that's just kilobyte in length. So it's a pretty big type. We're going to implement drop for big and just do something really silly, like print a message when the destructor is called. Then I have an async function foo from usize to usize. Doesn't really matter what it does. And then inside of my async function bar, we're going to construct a big simply to get the length of the array out, and then call foo with that length. So this is semantically equivalent, right, to calling foo with 1024. Let's say we don't want to repeat ourselves, and we forgot that consts was a thing in Rust. So we're just actually going to construct it on the stack and get the length out. And normally, the compiler could just optimize this away, and it would be fine. But what happens when we try to print the size of the state machine that bar returns? We're going to get something really big back. Our state machine's over a kilobyte in size. That's because it actually is embedding a copy of big inside of the state machine. The reason for this is that Rust has well-defined semantics for when destructors are run. And anytime you create a temporary inside of a statement, the destructor for that temporary is called at the very end of the statement. Basically, if you have a temporary expression inside of a larger statement, fast forward to the next semicolon you see, and that's when the destructor will be run for that temporary. Which in this case is not good, because that happens after our await point, right? So this is something to look out for, and it's pretty easy to mitigate. So in this case, we could simply get the length inside of one statement. There's a semicolon in between that statement and the next await. and that would be fine. We can also write it like this, actually constructing the entire foo future inside of one statement and then awaiting on the next line. It doesn't really matter. In either case, when we print the size of our state machine, it's going to be much, much smaller. We're not embedding a copy of big. Now you might say, okay, that seems like a problem, but if the temporary doesn't have a constructor, in other words, it doesn't implement drop, we should be able to optimize that away. Like, we don't need to hang on to this copy of big in between because we never need to call the destructor on it. And you'd be right, except unfortunately we don't do that optimization today. So that's kind of a future thing that we would want to do in the future. So for now, just always look out for big, complicated temporaries. This only comes up occasionally in practice, but it's something to be aware of. So, should you use async await? Yes, definitely use it. It's now stable, but it's a quote-unquote minimum viable product. That means that we're taking advantage of sort of the Rust release process where we release a new compiler every 6 weeks to iterate on the language and the compiler implementation. That being said, all of your code should, all of the state machines that get produced should be as good or better than hand-rolled in most cases, with a few notable exceptions, and that's going to continue to improve. I got to talk to some of the people writing the C++ coroutines proposal for 2020, which is a really interesting talk, and that's sort of their version, C++'s version of async await. And so there are a couple differences between theirs and ours. One major difference between Rust and the current proposal for C++ is that anytime we allocate anything on the heap in Rust, that allocation is always made explicit. So if you await another future, it always gets rolled up. All of the state for that future gets rolled up into your state machine, your data structure, and we don't allocate it on the heap unless you create a box and put the future in there. In the C++ proposal, there's actually an implicit heap allocation every time you await a future. And in many cases, the compiler can optimize that away, but there are no guarantees. You can't. There's a possibility to kind of trip over a new an optimization and have the optimization fail, and now you have a new heap allocation in your program in the C++ program. Rust has fewer language level extension points. So one consequence of releasing a new standard only once every 3 years is that you kind of try and shove everything in at once. This works for C++, but in the case of Rust, we kind of have a minimal service area. The benefit of that is that you have to do less work to keep your code performant. C++ gives you a lot of hooks and things that you can customize, but in Rust you just don't really need as much of that stuff. Another difference is that we're building on top of a newer language, so we have less legacy to do. Async await is not just for web servers. There are a lot of things you could use it for, and I think there are really a lot of interesting applications out there. One is high performance compute. Another is actually file systems. So anytime you're writing to or reading from disk, that's a whole lot slower than your CPU. So I think there's some interesting applications there. Device drivers might be an interesting thing. I'm working on operating systems, so that's kind of what I'm thinking about. Build systems. Anytime you are writing a build system, you're basically, you're starting like a compile step, and then that can take a very long time. So there might be some interesting applications there for expressing build systems and build rules. And UI is another way. So you can imagine showing a pop-up to the user and then awaiting their response, things like that. It's really just kind of a paradigm and a way of writing code that allows you to express what you want in a really high-level way. So it's not. If any of this interested you in terms of the compiler or just getting involved in the Rust project in general, I highly encourage you to contribute. There are lots of ways you can contribute. Probably the simplest way is if you hit an issue, whether it's a compiler bug or confusing error message, it's a great idea to file an issue for that. And there are people who do nothing except look for confusing error messages in the compiler and fix them, and they're awesome. So definitely report things. If you feel like picking up an issue to tackle, there's a lot of like easy or mentor tags in the Rust repo, so you can look for that. And take advantage of the community. I mean, one of the things I love about Rust is that it has a really strong community and people that are always happy to support you. So there's a few different places that you can go to kind of post, ask questions. There's me. You can find me on Twitter, GitHub, Gmail. And there are also working groups that you can join if you kind of want to have more of an ongoing contribution. Here's a short list of some working groups in the compiler team, but there's a lot of other working groups in other teams. You can find a list online. And that's everything. So we have time for questions.
You mentioned that Fuchsia's use of the generators prior to those optimizations being implemented was about like what, half megabyte on the stack or more. After the optimizations, can you share how much it shrank by?
Yeah, it's a good question. I don't remember that particular one. I think we shrunk it by, it's like by over 80%. Some of them, so some of the features that we had shrunk by like, well, didn't shrink at all, but some of them shrunk by like 80 to 90% in size. And so it just depended on how like deep the stack of features that were being awaited was.
The desugaring of the loop showed that it always like there's a loop and a match, so that even if you go from one basic block to the next, it would like jump to the top of the loop and rematch again. Is that how it actually compiles, or does it optimize it so that if you don't suspend the execution, it just falls through to the next basic block without jumping up to the top and then matching there, jumping back down?
Right. Yeah, so it does actually have a loop in there. So anytime you have a await, that is actually where the loop is introduced. Right. So anytime you await some like sub future, we basically pull that future in a loop. So what I'm doing is sort of semantically equivalent, but I'm putting the loop inside of the pull function, or it's around the body of our entire pull function, which is essentially doing the same thing. I'm just not embedding a loop at every single await point, because then it wouldn't fit on the slide.
So async await has been stabilizing for 4 years, right, or something like that. Now it's stable. So are you seeing something that might show us that that was a mistake? We should have waited a little bit more. No pun intended.
Oh. Uh-oh. So did we make any mistakes? I think time will tell. I think I'm really happy that we took the time to bake, even though a lot of people are understandably were upset by this. Yeah, I don't think that there's any like red flags or mistakes that we made. So some of the performance things that I covered, like the fact that we hang on to a temporary until the end of a statement, even if there's an await. That was a change that was introduced like a couple months before stabilization. And so I think that makes sense for the consistency of the language. That's how the language works outside of an async context. But yeah, it's possible we could have defined the language differently and just silently changed the semantics so that you don't hang on to temporaries across an await. Time will tell if that was right.
Hi, thank you for the talk. It's really interesting.
Thank you.
I'm curious about the state machine. Can you ask the compiler to emit either the, I guess not Rust source, but like the mirror for what the state machine it generates is?
Yes, you can. it's a nightly only flag, so you have to download the nightly compiler, and it's not super user friendly. What am I doing? Already going to show you. But yeah, so this diagram that I showed in the slides is actually generated by that. It actually emits like a .graph file, and you can render it. But so there's a couple different modes, but there's like Z emit mirror, and then like Z, I can't remember the flag, but message me and I'll send you the flag. There's a really nice documentation called the RustC guide, and it's for people working on the compiler. You can go find it there, even if you just want to see your state machine.
Well, thank you. Give a big hand to Tyler. So I wonder how many of you know that for every compiler change that might be stabilized, a full regression test is executed on every crate that's on crates.io. So everything is compiled, and every unit test in that crate is at least attempted to run. How many of you knew that? A lot. Can you imagine how much CPU time that takes for each and every change? It's almost hard to imagine. So using this process, we should catch all breaking changes to the language. Of course, not everyone open sources their crates, but well, we only do what we can do, right? And of course, if your crate does not have proper tests, then you're also out of luck. Should have better tests. So our next speaker, Pietro, is one of the maintainers of Crater, this system that does this regression test. And he's also a member of the release team, the infrastructure team, and the crates.io team. And he is going to shed some light on the gigantic effort that's put into releasing Rust. Give a warm welcome to Pietro.
Hi everyone, in this talk I'm going to shed a bit of light on how the Rust release process works and why we do it that way. As they said, I'm Pietro, I'm a member of the Rust release team and the co-lead of the infrastructure team. And I'm actually a member of other teams, but I do a lot of stuff in the project. And I think everyone is aware by now that we actually got a release out a few days ago with some feature everyone awaited for a long time. But that's not the only release. 6 weeks later, we released 1.48, which was released in September and changed a lot of code, hundreds of thousands of lines of code. And users just reported 5 regressions after the release came out. And only 2 of them broke valid code. The other ones were just performance regressions or worse error messages. 6 weeks earlier, there was another release. And this changes tens of thousands of lines of code, and we just got 3 regressions reported. And unfortunately, all of them broke valid code, but it's a very little number. And even before, we got 1.46 out in July, with just 4 regressions supported. And so, in the talk, I want to explain a bit why we do releases this fast, which creates a lot of problem for us, and how can we prevent regressions, and just get very few ones reported after the release is out. So, why do we have this release scheduled question is a bit interesting, because it's really unusual in the compiler world. I collected some stats on some of the most popular languages. And while there is some efforts to shorten the release cycle, like Python recently announced that they're going to switch to a year schedule, Rust is the only compiler, except for browsers, that's sort of popular and has a 6 weeks release cycle. And like in a compiler world, that's pretty fast, but there is a simple reason why we do that. We have no pressure to ship things. If a feature is not ready, we have issues, we can just delay it by a few weeks. And nobody's going to care if it's going to get stabilized today or in a month and a half. And we actually do that a lot. Like the most obvious example is a few weeks ago when we decided that async await wasn't ready enough to be shipped into Rust 1.38. Because turns out it wasn't actually stabilized when the beta freeze happened, and there were still blocker issues. So we will have to trash the feature and backport the stabilization, and that's something that we would love not to do. And we actually try to do longer release cycles, especially with edition. And it turns out we don't actually, it doesn't work for us. Like the edition came out, the stable edition came out in December, early December. And in September, we still had questions how to make the module system work. And we had a proposal in early September, which was not implemented yet. And that's what actually was released. But the proposal had no time to bake on nightly. Users didn't have much time to test it. And like it broke a lot of our internal processes. We actually did this thing, which is something I'm not comfortable still, which we actually landed a change in the behavior of the module system directly on the beta branch 2 weeks before the stable release came out. And if we did a mistake there, we will have no way to roll it back before waiting for an next edition. And we don't even know if we are going to do our 2021 edition yet. Like this request broke almost all the policies we have because we don't do this. But we had to do it because otherwise we wouldn't have been able to ship a fully working edition. And thankfully it ended great. The 2018 edition works. I'm not aware of any huge mistakes we made. But if we actually made them, it would have been really bad because we will have to wait a lot to fix them, and we will be stuck in 2018 edition with a broken feature set for backward compatibility reasons. So with such fast release cycle, how can you actually prevent regressions from reaching the stable channel? And of course, the first answer is the compiler test suite, because Rust-C has a lot of tests. We have thousands of them that test both the compiled output but also the error messages. And the test runs a lot. We have 60 CI builders that run for every pull request, and each builder takes like 3 to 4 hours. So we do actually a lot of testing. But that's not enough because a test suite can't really express everything the Rust language can do. So of course we use the compiler to build the compiler itself. Because for every release, we use the previous one to build the compiler. Like on Nitro, we use beta, on beta, we use stable, and on stable, we use the previous stable. And that actually allows us to catch some corner cases because the compiler code base uses a lot of unstable features and also is a bit old, so there are a lot of quirks in it. But still, that can't actually catch everything. And we get bug reports from you all. And we get them mostly from nightly, not from beta, because people don't actually use beta, because asking our users to test beta is something we can't really do, because with such fast release cycle, you just don't have the time to test everything manually with a new compiler every 6 weeks. And languages with long release cycles can afford to say, hey, test the new beta release, but we can't. And even when we ask, people don't really do that. So we actually had an idea. Why don't we test a user's code ourselves? And this is an idea that seems really bad and seems to waste a lot of money, but it actually works, and it's Crater. Crater is a project that Brian Anderson started, and I'm now the maintainer of, which creates experiments which actually get all the source code available on Crates.io and all the Rust repositories on GitHub with a cargo lock. So if you created an Hello World repo on GitHub or an Advent of Code puzzles repository, that's actually tested for every release to catch for regressions. And for each project, we run cargo tests 2 times, one with stable and one with and one with beta. And if the cargo test runs on beta, on stable, but fails on beta, then it's a regression. And we get a nice colorful report where we can then inspect them. This is the actual report for 1.48, and we got just 46 crates that failed. And those are regressions nobody reported before. And then the release team manually goes through each regression, if regressive crate. I hope we didn't break any of yours. And manually checks the log and then files issue. So then the compiler team looks at the issues, fixes them, and ships the fix to you all. And 1.49 went pretty well because this is 1.48, and we actually had 600 crates that were broken. So if we didn't have crater, there was a good chance your project wouldn't compile anymore when you update it. And this is something that would break the trust you have in the stable channel. So we know Crater is not perfect. There are a lot of issues. We don't test any kind of proprietary code because, of course, we don't have access to your source code. But also, we only test Crates.io on GitHub and not other repositories such as GitLab, mostly because nobody got around to write scrapers from them yet. And also, not every crate can build in the sandbox environment because, of course, we have a sandbox. We can't just run every code without any protection because it turns out people on the internet are bad. And it's not really something we can scale forever in the long term because it uses a lot of compute resources already, which thankfully are sponsored. But if the Rust usage skyrockets, we are really going to reach a point where it's not economically feasible to run Crater in a timely fashion anymore. And those are real problems, but for now, it works great. It allows us to catch tens of regressions that often affect hundreds or sometimes even thousands of crates. And it's the real reason why we can afford to make such fast releases. Without it, this is my personal opinion, but I know it's shared by other members of the release team, I wouldn't be comfortable making releases every 6 weeks without Crater, because they would just be so buggy, I wouldn't use them myself. So to recap a bit, the fast release cycles that we have allow the team not to burn out and to simply ignore deadlines. And that's great, especially for a community of volunteers, mostly volunteers. And Crater is the real reason why we can afford to do that. It's a tool that wastes a lot of money, but actually gets us great results. So unfortunately, I don't think I have time for questions, but I'm going to be around the conference today and during the Impulse days. So if you have any questions, you want to implement support for the open source repositories, reach out to me. I'm happy to talk with you all. And thanks.
Actually, you have some time for questions.
Oh, that's great.
So, yeah.
Do we have time for one question or two? Because I have actually two.
I don't actually know that.
Okay, so first question. You were hinting that maybe the edition idea wasn't such a success for us. Would you think that jeopardizes a possible 2021 edition of the language?
The main issue wasn't really the edition itself, was that we actually started working on it really late. So basically, we went way over time with implementing the features. And granted, this is my personal opinion, it's not the official policy of the official opinion of the project. But if we make another edition, I want explicit phrases that we won't accept any more changes after this date and actually enforce that, because we nearly burnt out most of the team with the edition. There were people that were just for months fixing regression and fixing bugs, and that's not sustainable, especially because most of the contributors to the compiler are volunteers.
Okay, I'll ask also my second question. So the second question is, for private repository, of course, you cannot run Crater, but how would somebody who has a private repository, a private crates setup, would run Crater, or is that possible now?
I mean, someone could just test their code on beta and create bug reports if the code fails, if the code fails to compile. We have some ideas on how to create a creator for enterprises, but like it's just a plan, an idea, and at the moment we don't have enough development resources to actually do the implementation, test, and documentation work that such a project would require.
So that would be necessary to support Creator in a private environment?
Yeah.
Okay.
Any other questions?
A lot of crates have peculiar requirements about their environments. Can you talk about how Crater handles that? And specifically, is it possible to customize the environment in which my crates are built on Crater?
So the environment doesn't have any kind of network access for obvious security reasons. So you can't really, like you can't install the dependency yourself, but the build environment runs inside Docker. And we have these big Docker images, which is like 4 gigabytes by now, which just has a huge list of system packages installed. So like if you know your crate doesn't work, and you can easily check with docsrs, because docsrs actually, since recently, actually uses the same build code of Crater. So like if it builds on docsrs, it builds on Crater as well. And if it doesn't build, you can file an issue probably on docsrs is the best place. And if our Ubuntu 18.04 package is available, we are just going to install the package on the build environment, and then your package will work.
Hello, thanks for the great talk. How long does it take to run Crater on all of the crates?
Okay, so that actually varies a lot because we are making constant changes to the build environment, changing virtual machines and such. I think at the moment running cargo test on the entire ecosystem takes a week, and running cargo check, which we actually do for some pull requests that, like if there is a pull request on the Rust repository that we know is risky, that can break code, we actually run Crater just on that pull request beforehand, and then we usually do cargo check, which is faster. It takes about 3 days. But that really varies, mostly because we make a lot of changes to the virtual machines.
Any more?
Thank you. Is it possible to supply the Crater run with more runners to speed up the process?
Like, I think we could, like, at the moment we are just in a sweet spot because we have enough experiments that we fill out the servers, but we don't have any idle time. And the queue is not that long. Like, if we had more servers, then the end result is that for a bunch of time, the server is going to be idle, so we are just wasting resources. And we have actually sponsorship from corporates, for corporations that actually want to also give us great aid. And so if we reach a point where the queue is not sustainable anymore, we are going to actually get from them first before asking the community. And also, like, Crater is really heavy on resources. Like, the moment I think we have 24 cores, and like 48 gigabytes of RAM and 4 terabytes of disk space. So like, it's not something that you can throw a small virtual machine and get meaningful results out of it.
All right, we're out of time for questions. We're going on to the next talk. Thank you. So next we have a slightly less technical talk about how humans interact with software development and some of the risks or pitfalls associated with that. Katharina is a long-time Rust community member working out of Berlin, and give her a big hand.
Nah. Yeah, Is that 1 second, Linux. Yeah. All right, sorry for that. I had it working immediately the last time, and now I was kind of confused why it caused problems. So thank you all for coming, and thank you for watching, and to one particular person on the live stream right now. I hope you've had a good RustFest so far. I know I have. I really liked the way that the talks were split across 2 days, because it gave me like more time to think about them and to talk to people about what I've heard. It was less like crammed, so big thumbs up to the organizers. I really like that. I've been given the sort of privilege to close out the talk track today, and it also means that I'm the last hurdle before lunch, so I'll try not to take up too much of your time. I want to take this opportunity to talk about something that's pretty important to me, and I feel that it should be more important to all of us as a community. So for those of you who don't know me, here's a quick intro. My name is Katharina Fey. I've been involved in the Rust community since 2017. I started writing Rust because I wanted to write a DNS server. Please don't ask. I'm currently a freelancer, and you can hire me, but please don't do it all at once. I write a lot of free software, and I'm also one of those people who says free software instead of open source. And also I like shaving yaks, and my current yak is emails. I will be giving a lightning talk later about this, by the way. I travel a lot, and I write some software, and I have a pet shark called Nibble, which is the smaller sibling to a larger shark called Bite. And so I think this tweet sort of sums up what I do pretty well. Please do at me. I don't really like doing questions on stage. It's kind of awkward for me. But you can send me an email, or for the 5 other people using XMPP, it's the same thing as my email. I'm at Space Cookie on Twitter, also known as the Hell Site. Or just come talk to me. I don't usually bite. So, this talk comes with a few disclaimers. The first disclaimer is, and this was already mentioned, that this is not a technical talk. I will try to visualize a few problems in the industry, and none of that really requires any code, just more abstract things. There's no code on the actual slides. Well, except for one. I recently used async std, and it was really awesome, and I just wanted to say that I really love it. Disclaimer number 2 is that this talk is not based on personal experience. Well, okay, it's not only based on personal experience. All of these issues can and do affect us all, and I think it is important that we talk about them. Disclaimer number 3 is that my slides are kind of boring. I wrote this talk as a sort of essay, and mostly the slides are a way for me to get through my speaker notes. I think it is more important to listen to what I say, and also the script is in the speaker notes, and I will upload the slides. The slides are mostly there so that you have something to look at. That's not my face. The talk also comes with a content warning for anxiety, burnout, and depression, and if you're one of those people who doesn't like content warnings, I invite you to grow up, please. So, there's a few things that I want to talk about, and at first glance, you might think that these issues aren't really connected, but I feel that they are, and I hope that over the course of this talk, you will come to agree with me that there's a larger perspective to consider, and maybe together we can start working towards a better world. I don't claim to have any answers, but I do want to start a discussion. But it'll be okay. It's fine. So, first of all, I want to talk about technical debt. What exactly is technical debt? Well, as Rust developers, you probably don't really know what that is. It's a term that only recently, more recently came up as large companies have started dealing with their technical debt. And unfortunately, this means that a lot of the discussion and talks about it happen as to how to get rid of it, not why it is happening. Technical debt is just like any other debt, but for the tech stack of a company. Generally, when developing systems, sometimes engineers take shortcuts or make bad choices. Stuff happens, and then poof, there's legacy code. Maybe someone was fired who understood it all, and then no one else can. Or maybe you had to push yourself to make bad decisions for a release or something. So either over time or sometimes with bad decisions, technical debt is created. Now, I want to run through a small example here. And again, this will have no code, but I think it'll sort of demonstrate how this happens. And I think this will feel pretty familiar. So take Foo Limited, a fictitious company. They ship their first product that does serverless cloud AI computing on the blockchain, and they're very proud. Unfortunately, to push out their product, they had to do some hacks. Some of the code isn't as cool as they would want it to be. Kind of looks weird and pointy. Some of the engineers want to go back and rewrite some of it to be nicer and have a nicer architecture. But the next funding milestone is due, and they also have a large client, Google, who would like to use their tech. So instead, they just kind of hack around it, and they ship this. They apply some duct tape. And get more money and do more cool things. But it does mean that the investors are now happy, but it also means that the work that should be done never gets done. What is happening here? Well, money from either investors or clients is exchanged for technical debt. So what then? When you start looking into why technical debt happens, or if you generally look into the issue, most of the articles, most of the discussion is how to deal with it. And I guess that's fair. A lot of companies have large technical debt issues, and it would be an obvious question how to get rid of it. There's some good resources out there to how to do this. And I don't really want to get into this right now. Some of it is just refactoring techniques, throwing away code, all of these things. I feel it's a space that's pretty well covered, and I don't think me sitting here or standing here and talking about it is going to add anything. Needless to say, I feel that if your company has technical debt, there are resources out there to learn how to deal with them. In my opinion, it is much more interesting to ask the question, why? Why is technical debt created? And so I started researching this a few months ago, I think, at this point. And really, there's a few reasons, but the most prevalent ones that I could find were these four. So, the internet says making sacrifices for a deadline, which was the example we just saw earlier. Bad decisions from engineers. Sometimes people make bad choices and then it bites them in the ass. Systems getting old or talent going away. Someone just leaves the company, no one understands it. And bit rot, which in this case means a module that gets refactored over and over and over again to do more and more and more things to the point where it doesn't really do anything well anymore, and it's not really understandable. Now, I will grant you that there's a lot of reasons why technical debt happens, but none of them are technical. They're all social problems. People make bad decisions sometimes, but it's in the framework of their company that these decisions become technical debt. Not letting your engineers go back and fix their mistakes is how you create technical debt. And honestly, the same kind of applies to making sacrifices for a deadline. If you, as a company, not an individual, have to write some hacks to get your product out the door, and then you don't go back and let the people who did those hacks go back and fix it, that's creating technical debt. And but it's not the engineer's fault. People don't really work in a vacuum. It's the people's fault who did the time planning and who didn't allow for the people that for the engineers who worked on this to sort of build a working environment where they can do the things that they wanted. Companies make a lot of decisions all the time, and some of them are greedy, I guess, and then after a while of doing this over and over again, they start to pay the price. So I want to run through another example with Foo Limited. And oh, by the way, I want to thank my friend Rebecca at hazelnutxyz on Twitter, who'd made these in like 2 hours notice, and my my design direction was engineering fuck up. So for the last example, you know, Foo Limited is doing pretty well. They have 2 clients, Oogle and Amadont. But those people, those companies, fictitious companies, of course, have their own cloud backends, and they want to use those and not your own cloud because of data security or something that your engineers did not really care about. But unfortunately, your product is a bit of a monolith. So there's a module in there that interacts with your cloud, and it can't really be removed. Really, the most sensible way of doing this would be to pull out something from your core and write like a thing that enables plugins for different clouds to interact with your core. But that sounds expensive. So why don't we just copy and paste some code and build this wonderful tech stack. And so again, being put into the situation where either you can do something right or do something fast, the fast way is the one that ends up with an unmaintainable code base. I want to take a small step back here and at least mention in part why I'm giving this talk. A few months ago, I was at a conference that I don't want to name, and I saw a talk there that I don't want to identify. And it handled the subject of technical debt and how throwing away things can lead to nicer projects. Instead of just refactoring, throw away your code. And for the most part, I really liked this talk, right up to the point where it fell kind of flat. See, it's always possible to add new things. And when you're tasked with doing something, you can either do it in a maintainable way or in a bad way. Depending on your situation, you will choose one or the other. But the question that this talk never dared to ask is there really always a need to add more things? Are potential clients really that important that you sacrifice whatever you're building to the pictures that I just showed you earlier? They look cute as graphics. They don't look as cute as, you know, hundreds of thousands of lines of C++. Don't get me wrong here. I'm not saying that writing features is bad or that we shouldn't make stuff. Like, what's the point of being alive if you can't write bad code? I simply take issue with the idea that an engineering department has to bend over backwards because some management people promised some other management people a feature, and the people who then have to do the work don't get a shot at either coming up with alternatives with more realistic deadlines or finding a nicer way of implementing it. And even if you look this as, like, if you leave this aside and you only look at the effects of technical debt, pretty much all the time the focus is on the company. And I did this in my own talk until this very moment. I focused on how does technical debt impact Foo Limited and not the people working at Foo Limited. Most of the articles that you'll find on the internet does this, or do this pretty much always. And the talk that I mentioned earlier did this all the way through to the end. Yeah, even some research papers do this. Productivity is the focus. So what kind of effects can any of this have on people who actually have to work with these systems and you know, are humans with feelings and actual limits? People talk about burnout pretty much often, very often, the same way that they talk about technical debt. This happens at conference talks and in online articles and, yeah, also some research papers. A lot of the stuff that you'll find is stuff like this. Articles that go into detail how you personally can prevent yourself from burning out. The issue of being overworked in your job is being put on you to deal with. In a way, this reminds me of climate discourse. You personally are responsible for killing the planet, not the system that you're forced to live in. I talked to quite a lot of people over the last few months when preparing for this talk about their experiences with burnout, especially in tech, how they tried to deal with it, what support they got from their companies or friends. Needless to say, I have a bunch of dirt on a bunch of companies now, so that's always fun. More importantly, it's a common theme, even when people describe their own burnout, not to focus themselves in that conversation. There were people I kind of had to pry it out of how their experience had been and what they had gone through. At times it felt like a taboo thing to even talk about. On a personal level, anyway. Most of them were pretty happy to discuss burnout on an industry-wide thing, and oh yeah, the tech industry really has a burnout issue. I'm personally, of course, never affected, but you know. Productivity, again, is the term that's most often used, and it frames the entire conversation about burnout, something that happens to individuals with regards to a company and the loss of labor that it causes. This is very common. The only real sources of this that take burnout seriously I've found were medical papers, and studying the negative effects that burnout can have on people with excruciating detail and charts and numbers of really just things that happen to people. There's no slide here because this is depressing. So instead of doing any of that, I want to be a bit more personal for a bit. Part of changing the conversation means giving people the space to share their experience. And so I want to be at least one person on a stage that takes the issue seriously. Burnout is losing yourself to a job that you hate doing. I lost my line. Whatever you do, it's never enough, but you also feel like you want to do more. You're not being compensated, whatever that might mean, but you're too greedy if you ask for more money, and you're letting down your colleagues if you ask for vacation days. Personally, I also notice my creativity taking a dive whenever I burn out. I usually make music or write stories, and yeah, it has happened a few times before. Burnout isn't something you even entirely realize is happening to you. Sometimes it makes people anxious, sometimes it means people cry themselves to sleep. For others, it means focusing so much on what they do, it becomes their whole identity. They think of nothing else, they speak of nothing else. They literally, their job becomes their life. How many people like that do you know? The phrase, oh no, I'm just stressed, but not like burnt out, is pretty common. And I guess for some, it would be admitting a kind of failure. I know it was for me. Why am I talking about this at RustFest? I can already hear someone complain about how this is way too political and you came here for the Rust. First of all, okay, everything is political whether you like it or not. But secondly, and I think more importantly, Rust is a young language, and the people who write Rust are largely people who do it because they think it's fun. We are a community that's built around hobbyists. The previous talk mentioned this. The compiler is largely being developed by volunteers. Some people are even learning Rust as their first programming language, and maybe a Rust development job will be their first gig in tech. I think we owe it to those people and to ourselves that we give these issues a stage and talk about them. Because Rust projects often don't have technical debt yet, but the management structures that create it still exist, and burnout can just as well happen on a Rust project as it does on any other project. Burnout is something that affects us all, and I feel that as a community, we need to talk about it because it's important. These issues aren't going away. So I submitted this talk in other part because I just generally saw how conversations about burnout went down most of the time. But it's the larger context in which this happens which I find concerning. The tech industry has a burnout problem, and I do have some charts in a second, and it kind of feels like most people in it are grasping at straws as to why it's happening or what we need to do to stop it. Now, I will say that finding actual numbers on, solid numbers on how many people in the tech industry are burnt out is incredibly difficult. I could find numbers that were more representative of the entire workforce, but there's I'm not sure how much you can actually extrapolate from that. there's a lot of numbers on, or there's a lot of like data on studying the effects of burnout on people. But so I guess this is like a single source, so if they're fucked up. But even if you apply margin of error, over half is not a great number. Interestingly enough, from the same set of data and the same sources and the same sort of methodology, this chart emerged. It doesn't say in the picture, but if you do a reverse image search, you'll find the same article that linked the first one. It's really interesting that rates of burnout in the UK versus the US versus the rest of mainland Europe, not something I would have expected. I'll say that. So what now? Say that you're a team lead at Foo Limited and you want to take this issue seriously, but you don't know what to do. You go on the internet and you find some ideas and you follow some popular discourse on what to do to help your colleagues or employees with their struggles. A lot of the discussion is about a 40-hour work week. This seems to be largely an artifact of US companies, in particular branding themselves as progressive for not having a 60-hour work week and explaining how much more free time you have in such a model. I live in Germany, and in Germany, for example, a 60-hour work week would be illegal because there's such a thing as labor law. Yet there are startups in Berlin right now that advertise their 40-hour work week as progressive and generous to workers. Another proposed mechanism is to make the office more friendly, add a ping pong table or foosball or a Nintendo 64 emulator. And, non-committal statements like, why don't we just try chilling it with the deadlines? Or, have you tried not being in so many meetings? And I feel that these conclusions are unsurprising, considering the lens through which the analysis of burnout is happening. Your focus, or the focus of these techniques, is on the productivity of a company. Think of your KPIs, not the mental health of your employees. Actual solutions to burnout would include things like switching to a 4-day work week, or even putting someone on several months of paid leave to recover, the same way that they would be allowed to recover if they had a severe physical injury. So if we know that there's good approaches for aiding people recover from burnout, why aren't these things that companies are proposing? Wouldn't you as a stakeholder in Foo Limited also gain from keeping your workers healthy and productive? What we end up with, what we end up getting are these fake solutions that make sure that people's recovery from burnout is always grounded in the office environment. You're allowed to recover from burnout, but please think about work in the meantime. Solutions that have been shown to work, like the ones that I just mentioned, but are expensive, are often not considered. Also, this screenshot is from a paper. There is a Sci-Hub link in my speaker notes. Please read it, it's amazing. There is a wider trend in our culture of seeking solutions that make everybody happy, sometimes called a win-win. It frames our ability to facilitate change as a quest to a solution that benefits those who need help as well as those who don't. You're allowed to address A, but I, as a stakeholder in Foo Limited, also need to benefit with B, is essentially how the conversation is framed. And so, discussions about burnout turn into conversations about productivity. Discussions about technical debt turn into conversations about productivity. This happens because the stakeholders of companies have a vested interest in letting the conversation go down this route. But there's a common thread here. When the stakeholders of an organization make decisions, people will end up in situations where they burn out, regardless of how well-intentioned they thought to have been. By being disconnected from the reality their decisions exist in, people will burn out. Analysis done through this framework is inevitably lacking and will fail to describe why these things are happening and keep happening, even though we know why. It's a work week that's way too long, deadlines that get made by people who are too detached from both how much work something is, as well as not actually having to do that work. Changing requirements, technical debt that already exists and keeps piling on, adding more stress to the people who need to work with these systems every day. And these things will keep happening as long as we don't fundamentally change the way that we work and can relate to it. So, what are the alternatives? What if the stakeholders of a company were the people doing the work? What if you remove management from the equation? Let the workers take control of their work. And when I say take control, I don't mean require a little oversight. I mean something much more essential. You might think that you're being overpaid in your cushy tech job, but even your high 5 or 6-figure salary is nothing in comparison to compared to what someone in upper management makes. And they hold power over you and your life that you will never have. When I say take control over your work, I don't mean you personally either. Get connected with your colleagues. Together you're stronger than you could ever be alone. You might think that your company needs you, but it's also exploiting you. So fight back against that. And honestly, unions are a great tool to achieve this. Working without bosses isn't entirely easy either. It requires organizational structures, and it requires everybody involved in a team or company to understand the relationships between the work that is being done and how power dynamics factor into the decisions that get made. When you work under management, the power dynamic is very explicit. Your boss has power over you. In a way, removing management from the equation means being able to better understand your role in group dynamics and how you relate to the work that you want to do. And lastly, and this is, I think, maybe the most important point that I want you all to take home, when we talk about burnout, can you please stop mentioning productivity? How often did you, and actually think about this, how often have you thought in these terms when you thought about someone burning out? If you thought about burnout being an issue in the tech industry, did you think about it being a danger to the bottom line? And how often in recent times have you legitimately thought that a win-win is something that actually exists, where you can help someone and then you also get help, or however that's supposed to work? None of the issues that I talked about exist in a vacuum. And you'll find that once you accept that we are dealing with a larger social issue that really only manifests in our little bubble of society in very particular ways, the world will look very different to you as a result. Thank you very much, and I hope you enjoy the workshops today.
Thank you, Katharina, for that talk. I would also like to extend a general thank you to all the speakers again for their wonderful talks. So give them a hand. Then also for the workshop organizers, of course, they are still not yet done, but those that have been, thank you. I would like also to thank the venue for their space. And also, personally, I would very much like to thank all the organizers that made this RustFest possible. And last but not least, I would also like to thank the sponsors. We have the gold sponsors Parity, Redshift, and Nervos. And our silver sponsors Embark, Holochain, Microsoft, and Moulvat. So the reason why I accepted being the MCs together with Dirk Jan is not entirely selfless. I also like to thank the supporters and the local organizers, of course. Sorry. So this year RustFest was in Barcelona, of course, but me and Dirk Jan are also trying to organize the next RustFest. The next RustFest, I'm going to announce it now, is in the Netherlands. Yay, loading! Yeah, it's still loading. Yeah. So we are still trying to get the venue nailed down. We have 3 candidates already picked, so we're almost there. But we know that's going to happen in the spring of 2020. So it's going to be way sooner than the previous RustFests have been following each other. Maybe we'll go to the cadence of like maybe 2 RustFests a year, but might be a bit much. But we're going to do it a little bit earlier this time. If you guys want to help, or if you need any help organizing your own conference, you can of course contact us. With us, I mean like the Rust Netherlands team, but also the Barcelona team, and we're more than willing to help you out with that. Following, I have several announcements to make. So the next 2 days are going to be the Impul days. Some of you are already going home probably, but for those that are sticking around, the Impul days are at this venue. I don't know if it's the same building. Yes, it's the same building. And it's going to start tomorrow at 9:30. The plan is to have like a start together, and that we then move off to our separate project, whatever you're planning to do with your people of the same project. Yeah. Then I have some more general announcements. So the eBPF workshop, it was listed as a 2-day workshop, but actually it's a workshop that's been given twice. So if you wanted to join that workshop, you can do so again today. If you leave this room, please take away all your trash so that there's less work for us as the organizers to clean it up. A gentle reminder again to not throw any glass in the bins. After we all leave this room will no longer be available. That means that the quiet room that's over there is also no longer accessible through this room. And also you cannot leave any belongings here. But the quiet room will be accessible using the stairs to the workshop and the other spaces below. Also, when we leave, we're not going to leave now, but when we leave, the door on the for you guys left will not be open, but the other door will be, and that's because we would like to have like 1 queue for the food and not 2 queues merging. Those not always go right. Also, the gluten-free bags will only be handed out if you ask for them. So instead of like having a pile there and people taking the gluten-free bags when they're not meant for them, you now have to ask for them. And finally, we're going to make another family photo because the photo of yesterday, the lighting was not that great. So if the people that would like to be in the photo also come back here again, and the speakers are also here, that would be great. So thank you all. I think there were all the announcements, right? That's right. Oh, oh, sorry. It's nice auditorium. Yeah. So thank you, and maybe have another applause while you're standing up.
If you don't want to be in the picture, don't worry. We'll ask once the general movement has stopped a little bit. Everybody else, gather in the middle.
So if everybody who wants to be in a picture, I would kindly ask you to come in the middle and be close as a family. And standing up, please.
Is there anybody still in the room that doesn't want to be in the picture? Please wave real quick. Okay, just on the stairs.
We'd also like to make one more picture with only the speakers and the organizing team as well.